So we have our first speaker, Frederic Paulin, is going to talk about counting and equidistribution in quaternionic Heisenberg groups. Please, Frederic.
So thanks a lot for the invitation. So after a supposedly good movie, you always have advertisement. This is the advertisement part of my talk. So what happened? So you're supposed to have, can you move it up? So you're supposed to see lots of circles. Big circles and then circles becoming smaller and smaller. And that's going to correspond to a top view of the world. And then you have a side view of the world. What do you have here? So you have big ellipses, lots of them, and they are smaller and smaller ellipses, and you have lots of them. Okay? End of the advertisement, and be patient, young Padawans. You're going to understand that later. So I'm done with that. So I'll need to recall a few facts about quaternion algebra. So I'm going to use Hamilton's quaternion algebra. I'm going to denote by HR. There are lots of H, okay, horosphere, hyperbolic, Heisenberg. All of these names start with H, Hamilton. Okay, sorry about that. So that's a set of elements X, which are the form X0 plus X1i plus X2j plus X3k. And the Xi's are in R. So this is a four-dimensional real algebra, which I'm going to handle with a Euclidean structure just by asking that I have an orthonormal R basis 1i jk, and the algebra structure is given as usual by asking I squared is equal to G squared equal to K squared equal to -1. Ij is minus ji, and ik is minus ki. Okay, and if you really don't like the fun of having a non-commutative algebra, so just remember that this contains C, which is just generated by 1 and I as a vector space. So this quaternion algebra comes with conjugation. Extending the complex conjugation, X bar. So you just change the signs of all the elements except the first one. And so this extends the complex conjugation, and then you have a trace map, which is the sum of X and its conjugate. So that's twice X0, and this extends twice the real part in the complex case. So remember, twice the real part is much more important than the real part. Okay, so in the Heisenberg group, I come to that. In standard Heisenberg group, twice the real part is the number which should appear. And then you have the norm in the algebraic sense, a map which sends the product of X with its conjugate, which is a sum of xi square. So corresponding to the Euclidean norm, so that's the square of the Euclidean norm. Okay, so that's the algebraic norm. It's called the reduced norm. I'm not going to say more than that. Okay, so I'm going to leave that here so that everybody is going to remember this. And I'm going to talk about the quaternionic Heisenberg group. as I said, too many objects start with H. So I'm going to denote it by Heisenberg group of H R. So the quaternionic Heisenberg group, that set of pairs W0 and W in HR times HR, so that the trace of W0 is equal to the norm of W. Okay, so this contains the real standard Heisenberg group. You just restrict your quaternions to C, and what you get is twice the real part of W0 is equal to the absolute value of W square. Okay, so I'm going to rely a lot on your presentation. So thank you, Luca Caponia, for these nice lectures, except that I'm going to change a lot of things, including the correct, from the arithmetic point of view, the correct definition of the Heisenberg group is twice the real part is equal to the actual value, and not the imaginary part, not twice the imaginary part, but that's life. From the arithmetic point of view. And I'm going to use the standard law, which is just when you multiply W0W by W prime 0 U prime. What you do, so the W just add them in the standard way. And here you start by adding W0 and W prime, and then you add the twisting factor. And what is important is that you have W bar, W prime in this order. So there is, we are not living in the world of the Bisounours, where we're living in the non-commutative world, and order has an important meaning. Okay, so this is a 7-dimensional two-step simply connected nilpotent Lie group. So it does fit on all the one of the groups that everybody in this room is supposed to love. So it has a split central extension of the following form. So you consider the imaginary part of the quaternion algebra, the set of Hamilton's quaternion algebra whose trace is equal to 0. And then you have the quaternionic Heisenberg group. And it maps onto the quaternionic Hamilton's quaternions. So this is a 3-dimensional space. Okay, so now the vertical fiber is 3-dimensional, and the base is 4-dimensional. So I certain way consider that this as being vertical, and this going to be horizontal. And I'm going to denote the vertical projection. So the vertical projection when you project horizontally. Everybody agrees with this convention? Somebody call it the horizontal projection when you project. Well, never mind. This is a vertical projection. Okay. And it has a nice distances, as everybody know. And this should be called the Seigen distance, and not the Korani distance. So sorry about Korani, but Korani itself in his paper is saying that this is due to Seigen. Okay, so one of my mission here is to convince people working in sub-riemannian geometry no longer to use Korani distance, but to use a Seigen distance. And since I'm always open to negotiation, if you call it a Eigen-Coronary distance, that's okay. Okay, and so I know that several people are already using that. But Eigen distance is what, for instance, Goldman has been using terminology. Okay, so sorry about trying to change your standard uses of the. Okay, so what is it? It's a unique left invariant distance on the quaternionic Heisenberg group such that the distance between generic point W0 to the 0 point, the unit element in this group, this is 4 norm of W0 to the power 1/4. Okay, so I remind you that norm is when you restrict to a real, that's absolute value square. Okay, so if you raise to the fourth, that's indeed you recover the square root of the absolute value of W0. Okay, and as everybody knows, so you have a vertical part and a horizontal part. So on the horizontal part, you have HR. On the vertical part, you have the imaginary part of HR. And if you want to consider a ball of radius epsilon in here, as usual, so horizontally, you have a ball of radius epsilon for the Euclidean norm I just defined on H and R. And then vertically, you have epsilon square for the induced scalar product on the imaginary part. Okay, so the first part of my talk is going to talk about state result about equidistribution of rational points inside my quaternionic Heisenberg. So I have to say that Pierre is a friend, Pierre Pansu is a friend and a colleague, but I totally disagree with what is written on his T-shirt. To be a geometer, therefore I am not at all, so I'm going to be fighting lots of analyst people here. You need to be more group, you do need to do more algebra, and especially more group theory. Okay, and there is going to be no analysis in my talk, but a lot of group theory. Okay, and because of Klein, don't blame me, blame Klein, who defined geometry as being group action, a study of group actions. Okay, so I need rational points. So what are going to be the rational points in HR? So I'm going to denote it by HQ. That's just going to be the Q algebra generated by 1, J, and K. Okay, linear combination of 1 IJK with coefficients in Q, and so all the xi's which occur here are rational. Okay, and I'm also going to consider the integral points. That's also useful. So I could take the just integral combination of 1 IJK, but for technical reasons, that's not the most convenient. So I'm still going to take IJK, but I'm going to take 1 plus I plus J plus K over 2 here. Okay, so that's called the ring of Hurwitz integrals. Yes. W, indeed. But norm of W, okay, that's half the trace plus the W minus but the trace is given by the norm of W. That's true. It does depend on W, of course, but the norm of W0, okay, you have two factors, x0 square plus the sum of the xi, okay, but x0 square is the norm of W square divided by 2. Do you want me to write a formula? If you have a norm of x, right? That's x0 square plus x1 square plus x2 square plus x3 square, okay? And that's the trace of x divided by 2 square plus the norm of x minus the trace of x divided by 2, okay? And so this is something related to the imaginary part of W0, okay? And the trace of W0, again, that's the norm of W, so it does depend on the norm of W. This is only going to be distance there, okay? You don't, I like simple formulas, okay? And this is a simple formula. And if you have other models of even that's also true in the Heisenberg standard Heisenberg group, huh? No problem. Yes. So this is very technical. You can forget about that at this level. So I'm going to do as less arithmetic as possible in this talk. You have generalization with definite quaternion algebras and maximal orders and things like that, but I'm not going to talk about that. And also everything I'm going to explain extends to higher dimensional quaternionic Heisenberg groups, and I'm going to stick to the two-dimensional one. Okay, so before defining the rational points, so I can consider the integral points. So in the Heisenberg group, I can consider the integral points of the quaternionic Heisenberg group, and that's just going to be the intersection, the set of points in the Heisenberg group, which are integral points. So the set of integral points of the Heisenberg group is a set of integral points of the Heisenberg group. And so this is interesting study in itself. You can study these things. And I just saw that last year at in the journal Annales scientifiques de l'École normale supérieure de Pise, Scuola Normale Superiore. So you just have a paper studying the Gauss counting problem on the Heisenberg group, expanding work of Garg, Nevo, and Taylor. So that's a very nice study, okay? What is the Gauss counting problem in the Heisenberg group? So I'm doing that in Heisenberg group. So here is an exercise for the session. Pick your quaternionic Heisenberg group and study the Gauss counting problem of these integral points inside the quaternionic Heisenberg. So the points I'm really going to be interested in are going to be the rational points. That is the set of points in the Heisenberg, quaternionic Heisenberg group, which are rational. And these points can be written in the following way. So any rational point, rational quaternion, is the quotient of two integral quaternions. You know that for numbers in R. That's still absolutely true. So you can write your elements as quotients, rational points as quotients of two integral points, except, remember, we now live in a very interesting non-commutative world. The usual world then is non-commutative. So we need to forget about commutative geometry. We need to work in non-commutative geometry. So the order is important. Okay, so the way I write it, A times the inverse of C is important. And I have two elements. So the second element, I'm going to call it alpha C minus 1, because when I have two ratios, I can reduce them to the same denominator. And that's what I'm doing. Okay, so ABC, A alpha C are integral quaternions. You need to divide by C, so C needs to be different from 0. This needs to be a point in the Heisenberg group. So this is just saying that the trace of AC bar is equal to the norm of alpha. And when you reduce to the same denominator, as in the real case, you want to reduce them in the most efficient way possible. So you're going to assume that A alpha C generates the left ideal generated by A alpha C is equal to the ring of integers in. Okay, so this is the left ideal generated by A alpha B and C. Okay, so that's my set of rational points. And again, you're reducing. Yes. Oh, okay, so I have divided by the inverse of an element here, x minus 1, that's x bar divided by norm of x, and that explains this. It's just a computation. I'm not going to do it, but the formula for the inverse, as in the real case, as in the complex case, okay, take the conjugate and divide by the square of the absolute value. Okay, so if you plug in here, you get exactly this formula. Trace of AC minus 1 is equal to the norm of alpha C minus 1. Okay, so yes, of course, the rational points are dense in the Heisenberg group. And one natural way is to estimate how dense are they. Okay. And so in order to see that, and that's going to be my first theorem, I'm going to put a Dirac mass at my rational point AC minus 1 alpha C minus 1. Okay, so that's the Dirac. That's my notation for Dirac, unit Dirac Dirac mass. And then I'm going to sum over all my rational points AC minus 1, alpha C minus 1, which are rational points in the Heisenberg group. Okay, so this is an infinite sum, so that would be bad. So I need a complexity for these rational points. And what is your favorite complexity for the complexity of standard rational number P over Q? Usually you take the denominator, okay, or the absolute value of the denominator. That's what I'm going to take. Okay, so I'm assuming that the norm of C is less than some S. Okay, so this is the height, an algebraic height of my rational point, and just going to say that the norm is the square of the absolute value in the complex case. Don't forget. Okay, and I forgot some very important thing, and I'm going to go back to that. So this is still a huge sum. As S goes to infinity, you have lots of elements. So you need to renormalize that. And you renormalize that by the beautiful constant pi 8 over 162, and then S to the power minus 5. And then this is a measure on my quaternionic Heisenberg group. And I claim that this measure, weak star converges as S go to plus infinity towards the R measure of my quaternionic Heisenberg group, where R is a unique R measure on the quaternionic Heisenberg group. And here I need a normalization. And so I renormalize it so that if I take the lattice of integral points in it, it has covolume 1. Okay, so I normalize it so that the quotient by the integral points has volume 1. That's a choice. Okay, when you have the circle, you can renormalize it so that it has length 1 or length 2 pi. So some people do some different choices, and I'm going to renormalize it so that it's okay. So that's going to be my first statement here. And you have a 5 which occurs here because I forgot something very important. So what is the Hausdorff dimension of the eigendistance on the quaternionic hyperbolic quaternionic Heisenberg group? It's exactly 10. Okay. Topological dimension is 7, and Hausdorff dimension is 10. That's the picture here proves that. Remembering that the fiber is a dimension free now. Okay, so we no longer have a contact structure here, right? And no longer have a CR structure here. We have what is called a hyper CR structure. But 10 is an important number. So remember 10 and remember the pictures of the advertisement. 10 is going to show up a lot of time. And the 5, which is here, is 10 divided by 2. 2 because here I have a norm, again, norm of C is absolute value square when I restrict to the complex numbers. And an obvious corollary is a counting corollary. So assume you want to count these rational points whose complexity, height, or whatever is less than S. So that's obviously an infinite number because you can always translate by the rational points. Okay, so I need to divide by the action by translation of the integral points. So when you add an integer, you don't change the denominator. You then change the complexity of the denominator. And this is equivalent to this 162 divided by pi 9 times s to the power 5. Okay. And how do you prove that? Well, you integrate this formula on a fundamental domain for the action of the integral points on the quaternionic hyperbolic space. Our measure gives, so you need weak star convergence is for continuous measure. So as always, don't forget to integrate on domains whose boundary as R measure 0. Okay, but you do have fundamental domains with boundary R measure 0. Okay. So that's the first part of my talk, first set of theorems. And the second part is I want to count arithmetic quaternionic chains that I'm just going to denote by them by chains. And I'm going to define them soon. Okay. So the point of this is that in order to fully understand even the standard Heisenberg group, it's linear geometry is not sufficient. You need to do projective geometry. Okay, so I'm going to talk a lot about projective geometry of the quaternionic Heisenberg group. And this is going to include projective geometry of the Heisenberg group. Okay, so that's the richer structure, right? When you want to study in the plane circles, okay, you can work with the group of isometries of R2, but that's not sufficient. If you really want to understand circles in R2, you need to pass to projective, complex projective geometry. Okay, so if you really want to understand the geometry of the quaternionic Heisenberg group, it's important to do appropriate projective geometry, which is going to preserve the extra structures that this Heisenberg group has. Okay, so I'm going to denote by H the map Z0, Z1, Z2 maps trace of Z0 bar, Z2 minus trace, sorry, plus the norm of Z1. So what is this map? This is a quaternionic Hermitian form of with signature 1, 2. On the right, vector space over the quaternions, and H are free. So Z0, Z1, Z3 are free elements, free quaternions, and Z0, Z1, Z2 are free quaternions. And if you don't know what it is, that's fine. Just don't forget that you have a copy of C inside that, and that's just a Hermitian form of standard Hermitian signature 1, 2. Okay. So it's not positive definite. Okay. So it has an isotropic cone. So it's isotropic cone IH. That's just the set of Z0, Z1, Z2 elements in the right projective plane over the quaternion. So so do you know why we should consider HR free as a right vector space, to where the multiplication by the scalars is on the right? No buzz. It's because you want the linear group. The linear group acts standardly on the left. Okay, but you want the linear group to act linearly, and the linear group acts linearly only if you take the multiplication of the scalar on the right, because you cannot switch the scalars. Okay, you have your matrices. You're going to multiply matrices by elements. Okay, if you don't multiply the scalars on the right, okay, then the linear group is not going to act linearly, which is kind of bad. So that's why I'm taking the right vector space, and then I take the modulo HR star on the right. So that's why I take the right projective space, and these Z0, Z1, Z2 are the homogeneous coordinates, just multiplied by a scalar on the right, same scalar on the right with free numbers. Okay, so isotropic cone, I want it to be in the 0 set of my Hermitian form H. Okay. And so why is this important? And I'm going to that. So you have one point at infinity, which is the homogeneous coordinates. You put Z2 is equal to 0. But if you put Z2 is equal to 0 and H is equal to 0, this forces the norm of Z1 to be 0 and Z1 is equal to 0. And then you can always normalize Z0 to be 1. And hence, what do you have? What remains is exactly the quaternionic Heisenberg group, where you're going to identify your couple W0 W with in homogeneous coordinate. As usual, the W0, W1, so that's the standard thing. You're also doing that in the standard Heisenberg group. Okay. So this isotropic cone, okay, turns out to be the one-point compactification of the Heisenberg group, which is a 7-dimensional real space and one-point compactification. This means that this is homeomorphic to the 7 ball. Okay. So this is a projective model of the Heisenberg group. And that's very important to use as much as possible this geometric model, because that's where, so geometry again, not Pierre Pansu's t-shirt. Geometry is group action, okay? And the group action, you understand it better on the projective model, okay? And what is the group you're going to consider? So for the projective unitary group of your emission form H, PUH of H R. So projective, because I take the unitary group and I divide by the center. So here the center is very small. You just have plus or minus the identity matrix, because it's hard to make things commute, because already in Hamilton quaternion, the center of the Hamilton quaternion is just the real part, x0. So since it's hard to make things commute already in the field, you don't say field in English, in the division algebra, it's even harder to make matrices commute. Okay, and UH, that's just a unitary group, that is elements of the linear group over H, three-dimensional linear group, which preserve this Hermitian form H. Okay, and in this, I have an arithmetic lattice, and I'm going to put arithmetic between parentheses, which is just going to denote by gamma, the set of integral points of this projective unitary group. Okay, so I take the integral quaternions and I look at matrices, 3x3 matrices with coefficients in the which are integral quaternion and which preserve the Hermitian. So arithmetic is not necessary here, because that's a theorem of Margulis-Gromov-Schoen. All lattices are arithmetic in the quaternion space. So I'm interested to studying chains, quaternionic chain, but I'm just going to say chain. So what is a quaternionic chain? Okay, so that's again, so it's going to be something that we're really going to see in the Heisenberg group. And the Heisenberg group lives in a projective space. So we're going to define the chains in the Heisenberg group by considering projective objects in the right projective space. So that's the intersection assumed to be non-empty and not reduced to a point of the isotropy cone IH with a quaternionic projective line so quaternionic projective line, so that's a 4-dimensional thing. You're going to intersect it with the 7-dimensional sphere, which is the isotropic cone. And this is going to be a 3-dimensional sphere. Okay, so so you cut in your 4-dimensional space intersection with a codimension 1 object here, and this gives you a codimension 1 object in the 4-dimensional quaternionic projective line, and this gives you something to S3. So you have two kinds of chains. You have the infinite ones, which are just the one which contains the point at infinity, and the infinite one are of the form infinity union a fiber of the vertical projection pivot. Pivot is vertical projection for the Heisenberg group to the quaternions. Okay, so these are the infinite chains, and you have the finite chains, the one who do not contain a point at infinity. So what are they? They are ellipsoids. So that's a 3-dimensional ellipsoids inside the Heisenberg group. I might forget to say quaternionic Heisenberg group. In the Heisenberg group, so whose image, when you project by the vertical projection, is just a round sphere in H in the quaternions HR. Okay, and so you have a nice polarity situation. So if people want formula, I can give you formula. So it's a set of elements in the Heisenberg group, of the projective model of the Heisenberg group, such that there exists some element Z0, Z1, Z2 in HR3, such that the Hermitian form is positive on that. And I take then the set of points in the Heisenberg group, which are orthogonal for the Hermitian form H to this positive vector. Okay, so that's minus W bar Z0, Z2, sorry, minus Z0 plus W bar Z1 is equal to 0. So where I have fixed a positive element here, and since I want this to be finite, and I also want Z2 to be different from 0. If Z2 is equal to 0, this is the equation which defines an infinite thing. You see exactly a fiber of the vertical projection. Okay? So that's going to be my quaternionic chains, which we talk about this morning. And I'm going to say that a chain is arithmetic if a chain C is arithmetic, if the stabilizer arithmetic with respect to the integral points, okay? And the integral points here, I have a lattice of integral points inside my Lie group, projective unitary Lie group. So if the stabilizer of gamma of C has a dense orbit on C. Okay, and so the theorem, second theorem is the following one. So take, obviously, if you take an arithmetic chain, and if you look at its image by gamma of this arithmetic chain, it's also going to be an arithmetic chain, okay? And since gamma is a lattice, it's an infinite group, so you are going to have lots of arithmetic chain. And one idea is to count. Let us count these chains inside an orbit. Okay, so I want to count the number of chains which are in an orbit. So let me call C0 an arithmetic chain. And from now on, I fix C0 an arithmetic chain. And I want to count them, but there are going to be, there are infinitely many of them. And when you iterate the group, their diameter for the eigendistance converges to 0. Okay? So I'm going to assume that the diameter for the eigendistance of C is bigger than some epsilon in order to have a finitely many of them, because again, when you iterate your group, your chains are going to become smaller and smaller. So I want to so this is still not still infinite, because if I use the integral Heisenberg translation, they are going to preserve the isometries for the eigendistance. Hence, if one has diameter at least epsilon, it's translated by integral points also going to be so to have diameter at least epsilon. So I consider them modulo the action of the integral points of my quaternionic Heisenberg. Okay, and then I claim that this cardinality is equivalent to a beautiful constant, but I'm not going beautiful and explicit, but I'm not going to give the form here. So epsilon minus 10 times 1 plus big O of epsilon minus kappa for so C and kappa, some positive constant. C is completely explicit and kappa is not explicit, and I'll come to that later. So that's going to be my second theorem of today. And that brings us back to two things that I ask you to keep in mind. First, the number 10, that's the same number 10 that we've seen. And then the advertisement and the picture we saw. That's okay. So it's hard to make pictures in 7-dimensional. I don't know if you know how to do that. I don't. Even in dimension 3, it's hard, but that's a standard Heisenberg group. So the picture I showed you are a slice of the quaternionic Heisenberg group, precisely corresponding to the standard, your standard Heisenberg group. Okay, and then the chains become ellipses. Here there are ellipsoids of three-dimensional ellipsoids, but in the standard Heisenberg group, the chains are just ellipses. Ellipses is that when you project them vertically, you have circles. So we had two pictures at the beginning. A picture which was view from the top. When you project horizontally, you have all circles which accumulate. And a view from the side, where you do have the vertical direction upstairs. And when you do see the ellipses. Okay? So this a proof of this theorem is given by the two pictures I've shown you before. Okay, so I need to talk about tools, and I'm going to talk about quaternionic hyperbolic geometry. So that's the first tool. And again, I'm very glad that we had a mini course by you, since so this is my geometric tool, and all the geometric tool is going to be passing to infinity in quaternionic hyperbolic space. And I'm going to normalize the curvature of it. So you have two choices, and I'm going to I'm a cat -1 kind of guy, so I'm normalizing then like that. It's a better normalization anyhow, because in your transparencies you have the factor 32, if you remember. Okay, 32 is strange, but why is this 32? 32 is because that's 2 times 16. Why? And 16 is 4 square. Everybody is following me, huh? Okay, but the curvature, upper bound of the curvature is -1/4. So that's 2 times the square of the inverse of the curvature, your factor 32 here. And I prefer to normalize it so that your factor there just become 2. That's why I'm choosing that. Okay. Yes, what is a quaternionic hyperbolic group? So again, the better model to do geometry equals groups. Sorry, Pierre. And for group action, the better model is a projective model. So the set of points W0, W1 in the right projective plane over Hamilton quaternion, such that minus the trace of W plus the norm of W is negative. So that's fine because when you pass to infinity, that equal to 0. That's good. You recover the isotropy cone, hence you recover the Heisenberg group. So as time flies, I'm not going to give a formula for the Riemannian metric, but it exists, and I'm not going to use it. So it has. It's important to not define. Okay, a Riemannian manifold is not just a set. A Riemannian manifold is a set endowed with manifold endowed with a metric. Okay, so it's always important to define the metric. But the important point is that boundary at infinity is exactly the isotropic cone of H, hence the one-point compactification of the quaternionic Heisenberg group. And yeah, and it's much, that's again a reason, not the imaginary part of W0, but minus twice the real part is much better for arithmetic purposes. So it's isometric group. The full isometric group here is PUQ, so it's more restrictive than the complex case. And I'm going to need to consider oroballs there. And my favorite oroball centered at infinity. Oroball starts with an H, so sorry about that. This is bad talk. Too many objects, mathematical objects in my talk start with H. So I'm going to take the oroball set of points which have a certain height, and the height is going to be 2 n of W less than 2. Okay, and 2 is better than 1 because trace is twice the real part. So that's the appropriate normalization. Okay, so I'm going to draw a picture. Yeah, I'll need a picture. Anyhow. So the picture is the following one. So horizontally, I put the Heisenberg group. And vertically, I put the extra dimension that I need to pass from the Heisenberg group to the hyperbolic space. So this is the point 0, 0, 1 here, or the point 0, 0 in the Heisenberg group. And then up there, I have infinity, which is 1, 0, 0. And my Heisenberg, my oroball H is something which has height, which passes through the point 1, 0, 1. Okay, So H is what's above. And now chains. Yes, I need to go back to chain. So what is a chain? How do we understand geometrically a chain? So a chain, a quaternionic chain, that's a boundary at infinity of a quaternionic geodesic. Of X of my quaternionic hyperbolic space. And what is that? That's just the intersection of X with a quaternionic projective line and that's more or less the definition of a chain. Okay, take the intersection with the isotropic. Okay, so I have L. So I'm going to denote my quaternionic geodesic L and my chain by C. So I have my the chain C is a part at the boundary at infinity of my quaternionic geodesic. Quaternionic geodesic are four-dimensional spaces that open subsets of quaternionic projective lines, and they are actually isometric up to a multiple with the real hyperbolic space of dimension 4. Okay, so you have a real dimension hyperbolic space of dimension 4, and boundary at infinity is just a chain. Okay. And so the arithmetic notion of a chain that was saying arithmetic, same thing as saying that if I take the quaternionic geodesic modulo is stabilizer, this has finite hyperbolic volume. Okay. So now, how do we relate the geometry and the arithmetic I want? So I want to let the group act, my lattice act, gamma. So there are 3 by 3 matrices with coefficients in the quaternions. And just look at the first column, and I'm going to denote them by A alpha C, the first column of my 3 by 3 matrices. I don't care what there are. And I'm going to assume that they do not fix infinity, which is equivalent as saying that the factor C is different from 0. So then I'm claiming that gamma infinity is exactly AC minus 1, alpha C minus 1, the points which belong to the set of rational points of the Heisenberg. In other words, this describes the set of rational points with, I started 2 minutes free. I'm going to leave time. So I just need 4 minutes more. Yes, so my rational points are just the orbit points of my infinity under the lattice, and the complexity is, so I have a point gamma infinity here, and then I can consider gamma h, okay, and the distance between these two oroballs, h and gamma h, is going to be exactly log of the norm of C. So the complexity of my rational points can be read on the length of the common perpendicular here. And that's the first point. My second point is that the distance between, so in the same way, I have the distance between H and the image by gamma of L, and that's going to be minus the log of the diameter of the eigendistance of H of gamma C. Okay, and so how do we prove now the statement? I'm just going to finish by stating the result. I'm going to use an analytic dynamical system tool, equidistribution of common perpendiculars. So you see my objects on the Heisenberg group. Okay, I control them by common perpendiculars, and I'm going to denote by D either H or L, quaternionic geodesic, which is arithmetic, and then and I'm going for every gamma in gamma modulo the stabilizer of D. I'm going to denote by X gamma. That's in the boundary of H. So that's the point here, X gamma or X gamma here. So that's the origin of the common perpendicular from H to gamma D. Okay, and I'm going to end up with my statement, which is going to prove everything. And then the theorem is that there exists positive C, so that C times the volume of the quotient of my quaternionic hyperbolic space modulo the lattice gamma divided by the volume of D modulo gamma D times exponential minus 10 T, the sum of the Dirac mass at all these points X gamma for gamma in gamma modulo gamma D, and the distance between H and gamma D is less than T, which star converges to the volume on the boundary of this Europe. And I'm going to conclude that. So 10, again, is the same 10 as the beginning Hausdorff dimension of the quaternionic group. The volume, the boundary of the horosphere is very homogeneous. Okay, so if you push forward, you're going to map the volume here to some invariant measure, left invariant measure on the Heisenberg group. So it's a multiple of the R measure. And again, this Dirac mass here, this parameter, when I push forward, I have a Dirac mass at gamma infinity. And when I want to count the chains, I just integrate these, and I need to compute these constants here, which require lots of work, but I'm going to stop there.
Thank you very much. Thanks. Are there questions?
In some of the statements, you seem to really use that the lattice is non-uniform.
I am definitely using that lattice is non-uniform. Yes.
And are there analogous things you could try and prove in the other cases?
Yes. Instead, so I'm definitely using that this robot here is co-compact. But if I can replace D H by some D prime, so another arithmetic chain, and count common perpendicular between two orbits of quaternionic geodesic lines. Yes.
I'm going to ask one more, which is just, has all of this already been done in the complex hyperbolic world?
Yes, we've done that previously.
Okay.
But I already gave a talk some 5 or 7 years ago on the complex hyperbolic case. So that's why I switched to that. And I kind of like the non-commutative world too. But you can take what I explained, replace quaternions by C, and it works exactly the same. Well, no, you have much more work in the quaternionic world because just computing these volumes are very hard, right? You need to use Prasad volume formula. And for those who know what is Prasad volume formula, you need to look at all the local places and compute local constants over QP or for some strange P's. And that's a lot of work. So most of the, almost half of the paper was computing purely algebra group, computing this volume, and proving that here I have a statement, an orbit point gives me a rational point, proving the converse is surprisingly hard, and actually false. I'm using nice things about the Hurwitz ring of Oettinger, that is the principal ring. You say unique, UID. I don't know how you say that in factorial.
So welcome back, everyone. Now it's time for the talk of David Fisher. He's going to talk about Tukia type theorems for Carnot-by-Carnot groups. Please, David.
So it's really a pleasure to be here at this conference. It's been great so far. I'm sure it will continue to be so. And I actually was last in Pisa at the age of 12. So it's also fabulous to be back here because I know it's a great place. And so I should say that I'm going to start with some work that makes me feel old because it's older, to motivate the work that is new. And when I get to the work that's new, it's joint with Tullia Dymarz, who will give the sequel to this talk after this talk, and Zhang Dengji, who I think is in the room somewhere, but I'm not finding immediately. Oh, there he is. So all the tough questions go to them, not me. So just because it has sort of been right at the periphery of the conference so far, I guess I should just mention briefly the Gromov program, and which is what motivates this particular work, which is program is classify finitely generated groups up to quasi-isometry. I do plan to take advantage of the many lectures that come before mine and not define things like quasi-isometry or Carnot group. If anyone needs a definition, they should just ask for it. If you need anything, just ask for it. But we want to classify finitely generated groups up to quasi-isometry. This is a program put forward by Gromov in the early 80s after he proved some very stunning results about it. One should say that actually, classify is a bit much. It's actually an undecidable problem to classify them all, but you want to classify where you can. And so where you can, for me, and this relates to the Cornelier's talk a bit, is really about, so let's take gamma, a finitely generated group. Now we'll take G, a Lie group. Before Frederic is picky at me, a connected Lie group, since otherwise gamma is already a Lie group. And you can ask, what gamma are quasi-isometric to G. And I don't know that this actually is written anywhere in the literature as this, but certainly I think everyone who's worked on related things believes the following conjecture that, if gamma finitely generated is quasi-isometric to a connected Lie group G, then gamma is a co-compact lattice in some, potentially other Lie group G prime. And this conjecture is, sort of the quasi-isometry version of Mostow rigidity. There's an analogous theorem. Everyone states Mostow mostly for real hyperbolic space or hyperbolic spaces or simple Lie groups, but Mostow actually considered all connected Lie groups eventually in his papers. And so this is some sort of generalization of Mostow rigidity to quasi-isometries. And there's a lot of progress on it. For instance, if G is semi-simple, then it's been done for a while, and I won't mention all the names because I don't think, Pierre's in the audience. Pierre's one of the names. I don't think anyone else is in the audience yet. In that case, and the nilpotent case is due to Gromov. It follows from the polynomial growth theorem, and there have been various talks, including Pierre's, about what one might do and think about with that. And Eve, both some of the things in their talks were motivated by that. And then the question is, where did one go from there? Where does one get stuck? And when I first entered this field, where one was stuck was at a very simple group whose name is Sol, and somebody, I think it was Eve, already wrote Sol on the board, but this I will repeat. Take the semidirect product of R and R2, where this is going to be T for me, this is going to be X and Y, and I want to act by e to the T, e to the minus T on X, Y. That's the semidirect product. And this thing then has a Riemannian metric that's dt squared plus e to the T, e to the 2t dx squared plus e to the minus 2t dy squared. And I want to wave my hands at the geometry of this thing for a minute. Maybe I'll even write some things down briefly, just because we'll be generalizing this geometry today. We'll actually refer to a class of solvable Lie groups as Sol-like, and that'll be a definition soon. But what's the geometry of this thing? If we take, if I let y be constant, then the resulting sort of xt plane is the hyperbolic plane. You might not recognize it immediately in this model, but it's it's the log model of the hyperbolic plane. That's probably the least standard one, but that's what it is. And the yt planes, where x is constant, these are also hyperbolic planes. But in some sense, upside down. Right? If you think of the upper half space model, you think of the point at infinity as being up. And if I've got my orientation right, I could be flipped upside down in my talk, but you should fix that if I am. And one of these foliations is by hyperbolic planes where the point at infinity is up, and one of them is by hyperbolic planes where the point at infinity is down. And so you have this sort of mixed geometry of hyperbolic spaces, but they're the thing one should know about this space is what made it hard to study it in the first place is that it has directions of positive curvature. We're not in the Gromov hyperbolic world at all here. And this adds difficulties of all kinds and makes life very difficult. And so the old theorem that I promised you that I will stick in the corner here, which is by Eskin, myself, and White, is that if gamma is qi to Sol, then gamma is a lattice in Sol. There I don't have to change the Lie group. Just because it's too small, there's no room to change the Lie group. And when we did this, it was the last three-dimensional geometry for which this kind of result was unknown. It was the first solvable Lie group that was not nilpotent, for which this was known. It was some kind of event much in the ancient history of my life. The publication date is 13, but I can complain about how long that took privately over drinks if anyone wants me to. The theorem was proved well before then. Yeah. So but even the publication date is 10 years ago, so maybe I should just pretend that's when it happened. And now we want to generalize this geometry. Oh wait, maybe yeah. Well, let me give you a proof sketch first. And the proof sketch, I give you the proof sketch because the proof sketch is somehow standard. And if there are young people in the room who haven't seen parts of this, you should see these at least once in your life. The first thing is, even, it doesn't really matter if I take sol or x, this part of the zero step in the proof sketch works for any metric space. And is what one does in many situations, and is probably an observation of Gromov's if it's not older. And now, I have that gamma is quasi-isometric to x, and I want to give this name a map. And though Eve was picky about it, I will just cheat and call its inverse F inverse. This is not an inverse in the literal sense of set maps. It's a coarse inverse, so the composition is only at bounded distance from the identity, but let me just cheat. And then, what I can do is, gamma acts on gamma by left translation. And as long as I have, which I always do, taken the right Cayley graph, and this is by isometries. So gamma acts on itself by isometries. And what I can do is, and we'll call, L gamma that action. I can take, what do I want to do? I want to take F inverse composed L gamma composed F. This gives me a map that sends gamma into what I'll just write as Qi of x. And again, I'm going to be fuzzy here because it won't matter once we get to anything technical. The set of quasi-isometries, because the composition law is only defined up to bounded distance, is not really a group. You should mod out by that equivalence relation. You should be more careful than I'm being on the board. But I get a group homomorphism there once I do the right thing. And so, studying this reduces studying groups Qi to x to studying self-quasi-isometries of x. Doesn't quite reduce it, but it makes it a step. You want to understand groups of quasi-isometries of x. You no longer need to keep the other side. And now, it's really the first step in Sol is to prove that the foliations by t, x, and y cosets or lines are preserved. So there's all this obvious structure in that space. There's the vertical lines, or what I'll call the vertical lines that are given by the R parameter. There's the X lines, there's the Y lines. All of those things are preserved. This is actually the main part of our work. What we did was this. And the second step is, this reduces the question to one about quasi-similarities of R, and you quote a theorem that in some sense is really due to Hincanen, but you quote a modified version of it that's the modification was enacted by Farben-Mosher for a slightly different purpose. And this finishes the proof of that theorem in the course outline I'm giving you. And yeah, what we want to do is be able to generalize this, and I'm going to start slowly because, it turns out to be harder to generalize this than we'd like. But I want to call a Lie group Sol-like if it's given by the following data. One is we'll have N1 and N2 nilpotent Lie groups. Two will have alpha I contracting automorphisms of the Lie algebras. And then 3, I will form the semi-direct product, R semi-direct product, N1 times N2, where the action of T on the variables N1 and N2 is, T acts as e to the minus T, or e to the T alpha I N1, comma, e to the minus T, that's alpha 1 N1, T to the alpha 2 N2. So I'm going to do exactly what I'm doing in the picture. I'm going to take N1 and I'm going to contract it as I go up. I'm going to take N2 and contract it as I go down. And now, because I was explicit there, I'll just wave my hands at it here. You can look at, there's sort of subspaces in here that look like R semi-direct and I sitting inside this group whose name will now be G. They're cosets that look like this. Those cosets, this group is what Yves talked about quite a bit in his talks. It's a Heintze group. It's a space of negative curvature. It's not quite a hyperbolic space. And there's one of the problems for us is there are really a lot of these. I mean, Heintze proved a theorem that said if you want a homogeneous space of negative curvature, it should look like this. But then if you really want to get your hands dirty thinking about these objects, and you saw this in Yves' talks too, you can't even quite classify these things up to quasi-isometry. And I've got some complicated thing built of multiple copies of them. And I will just quote my friend Mark Berger, who said to me at some conference somewhere, he said to me as I was talking about stuff like this, he said, I'm really glad I never studied solvable groups. There are too many of them. And so I'd like to stop here and say, okay, now we've proved this theorem about solve for sol-like groups. I'd like to be able to say that. I can't say that. But and there are good reasons why I can't say that. Maybe I'll state sort of a special case of the conjecture I just erased, which says that, if gamma is qi to g and g is sol-like, then gamma is lattice in some g prime where g prime is also sol-like. But even here, you already run into this problem that the Lie group might change, which goes back to Yves' talk where, you did one or two Lie groups quasi-isometric. This is one of the motivations for studying that question is because it just comes up if you want to study when discrete groups are quasi-isometric. Even if you don't want to study Lie groups, you're forced to. And now I want to tell you about this class of groups we're actually going to consider. And the first thing is just a remark, I guess, that, from now on, we're going to assume the alpha I are diagonalizable. A priori, there might be Jordan blocks. Jordan blocks make the geometry slightly more complicated. I don't think I'll get fuss from either my co-authors if I admit that, at some point we stopped thinking about the Jordan blocks. Then we wrote a paper and we never wanted to take the, you could, there's a paper Tullia wrote with Irene Peng where you could probably put the Jordan block back in by combining that paper with ours, but ours is already really long and that's already really long. And then it would be, becoming unreadable. So we just didn't, I don't think this assumption is essential, but maybe it is. Maybe there's more here than I think. And so now what I'm going to do is restrict the class of N's to a sort of tamer class than all possible nilpotent groups. Because again, why are there too many solvable groups? There are too many solvable groups because there are actually too many nilpotent groups. There really are a lot of them. And the class that we've liked here a lot is the class of Carnot groups. I guess, I think technically, even proving this conjecture where M1 and N2 are Carnot, it's contained in our papers and had not been done previously. Some of those results we think are maybe not as novel, but it's even new in the case where M1 and N2 are Carnot in this paper. It certainly was not written anywhere, but the real novelty is in a slightly more complicated case. So, maybe I'll write it as theorem 1. Anyway, theorem 1, let's call this conjecture A. So theorem 1 is by conjecture A is true if N1 and N2 are Carnot. There is some novelty in that. There's less novelty in that than what I'm going to say next. For what I'm going to say next, I need more data. The G prime M1 and N2 will also be Carnot, yes. That being Carnot will be invariant. And maybe, yeah, okay, I guess, I'm yes. I think yes in general. I think there you will have to change the group sometimes, yes. Yeah, no, yeah. Neither Tullia nor Zhangdong is contradicting me, so I'm probably right when I say yes. I'm getting a little blackboard blind. Yeah, no, I think you have to change the group even here. And yeah, so now we get to a slightly technical definition that I never quite get organized right in my head, which is why I'm hesitating. So I wanted to define what it means for N to be Carnot-by-Carnot. And maybe I should have broken some of this out of the definition, but I always put it in the definition, so bear with me. So first, what I want to do is I want to look at W in N, which is the Lie algebra generated by the eigenspace with smallest eigenvector. Right. I am taking this contracting automorphism. I really should say it's not a property of the group itself, it's a property of the group and the contracting automorphism. And now I can just look at the Lie algebra generated by the smallest eigenvalue. And if you think about this for even a few seconds, that's a Carnot group, just by definition. So W, or if you prefer, W, which is its exponential, yeah. Of one and I, yeah, just one. Knock the product. Yeah, no, we want to treat the two factors differently and get sort of two spaces of negative curvature. So W, W here is I said it was a Lie algebra, so it's the Lie algebra of some W is Carnot. That's not me assuming anything, that's just a fact. Because I generate it by the smallest eigenspace. And then we assume, in addition to things, we assume that W is normal in N. And 2 is we assume N mod W is Carnot with the automorphism induced by alpha, right? You have an automorphism of the space, you have an invariant subspace, you get an automorphism of the quotient. And so, this is the simplest thing you can do that's not Carnot somehow, right? You want something Carnot, you want something that's not Carnot. So what do? You take something that has two steps, each of which is Carnot, and the quotient makes sense. And each of these is an assumption, right? The thing generated by the smallest eigenvalue need not be normal in the group if you write down arbitrarily complicated examples, and the quotient need not be a Carnot group. So these are two assumptions about the algebra and geometry of these spaces. And then how am I doing on time? So what should I do next? When I say it's Carnot with the automorphism induced by alpha, I guess I mean that. Yeah, yeah. You know, you can, yeah. Now you're being picky. That's his job. Yeah. No, I mean, I want, you know, there is, you know, for a Carnot group, there's only one dilation, or rather, there's only multiples of one dilation. So I really mean that alpha is the Carnot dilation, right? I'm always talking about the data of the pair, and I somehow can't overcome my desire to be sloppy about that. No. Oh, yeah. Oh, yeah. No, it is. She's right. It is important that the first eigenvalue is 1 or is normalized to be 1. Yeah, you should normalize the first eigenvalue to be 1. Yeah. Yes. No. This. Yeah. Okay. There's a certain sloppiness about this. Maybe I should say a little bit about. I'll give you 2 examples where things are Carnot-by-Carnot that may clarify how I'm confusing people. The first is just R2. You know, this is X and Y. And I just want to take an automorphism of this. And instead of doing the thing that you want me to do, which is to scale them both at the same way, I can just do, you know, e to the tx, e to the 2ty. And then, you know, this is no longer, you know, R2 is a Carnot group. But with this automorphism, it is not a Carnot group. It's a Carnot-by-Carnot group because, you know, clearly this is the space generated by the first eigenvalue. That's the space generated by the second eigenvalue. The quotient is normal. Everything's fine. This is what I mean to be happening. And then, you know, it'd be slightly, you know, so there are 2 points of view on this. One is that's already new. This example I will say is the theorem that I should have stated or will state soon is contained first at partly in Tullia's thesis and partly in later work of Tullia and Zhangdong. Even this case, to completely understand it is complicated and takes a lot of work. So like you shouldn't underestimate that example. And the second thing I should say is, you know, this is maybe a little less fun for people who like nilpotent groups less than more than the like solvable ones, because, well, you know, this R semi-direct R2 is not the standard one that where I scale both factors the same. It is the same nilpotent group, and you can also define nilpotent groups that admit no Carnot dilation but are Carnot-by-Carnot. And the easiest one, you know, this will be the exercise for those who want to do something else in the rest of my talk. If I take the group that I get by taking 1, 1, 1, X, Y, Z cross all parameters real, and I divide by Z equals C, and call this group N. N admits no Carnot dilation or no Carnot automorphism, but a Carnot-by-Carnot one. Probably in this audience, I can just say this is a central product, right? It's a product where I divide out by the center, something funny in the center. And you know, what goes wrong with trying to make it Carnot is, it's clearly generated by the x, the y, and the a's. And if I try and scale them all the same, I'll end up scaling z and c differently. That's what goes wrong with making it Carnot. But if you want it to be Carnot-by-Carnot, it's not hard to arrange. And you can then, the second half of the exercise is generalize this a lot. There are a lot of examples that are Carnot-by-Carnot. So the theorem has large amounts of content, both in the case where you take things where the nilpotent group is simple and other content where you make the nilpotent group more complicated. And there are even more complicated examples in the paper for people who think, there may be people who think, oh, central products, that's too easy. There are other ways to build these things. So theorem 2. What does this say? It says, and again, this is by the three of us, says that, and I've erased it, but I'll still refer to it, that conjecture A is true. If N1 and N2 are Carnot-by-Carnot. I managed to get a little confused while preparing the talk and tried to convince myself that I could get away with only making one of them Carnot-by-Carnot. And for a little while, I thought I could, and then I can't. Yeah, no. So what should I say about this? I want to talk a little bit about the outline of this one, because it will, it follows the same outline as before, right? So outline, first, gamma qi to this g gives us a map from gamma to quasi-isometries of G by this old idea of Gromov's. That's step 0. Step 1 is any self-quasi-isometry of G preserves the coset foliations by R N1 and N2. And here I will just admit to my sins. This is, it's not very different than the case of Eskin, Fisher, and White, but we never wrote it. Already in Irene Peng's thesis, she quotes some generalization of this, just where N1 and N2 are copies of Rn, which we also never wrote. And so if you don't like the fact that we never wrote it, Tom Farragut will later in this conference talk about a result in much greater generality than that, where he proves, well, most of this. He's done most of the work, and he promises me he might eventually do the rest of the work of generalizing this to a much greater generality. And just to give you a slight preview of Tom's talk, I have these Heintze groups, these R semi-direct N1 and R semi-direct N2. They're spaces of negative curvature. Why do I want those spaces of negative curvature to be Lie groups? Why don't I just take two Gromov hyperbolic spaces and have them interact in the same way? This is the right generality to write this proofs in. What Tom is doing is absolutely the right generality to write these proofs in, and he's doing it, and it's great that he's doing it. And it's slightly embarrassing that we didn't do it in the special cases where we knew how. We definitely did not know how to do what he's doing, but we knew some more special cases than we wrote. And then the main import of what Zhangdong Tullia and I do is this reduces to a question about groups of quasi-similarities of Carnot-by-Carnot groups. And when we say Tukia type theorems, it's this. There is a theorem of Tukia's that's related to this that I will state in a little bit, or Tullia will state if I don't get to it. But this is the meat of the work in the joint papers by the three of us, is studying these kinds of things. We have some partial results when the group is not Carnot-by-Carnot in a first paper that appears on Archive 2nd, and we have a complete result in the Carnot-by-Carnot case that allows you to finish the proof. And we will explain that as we go on. But before I explain that, I want to advertise a question that, since I'm admitting to my sins, I'm going to admit to another one. Something that Eskin and Peng was Eskin's student in my postdoc and has since left math, something we worked hard on for a while and never finished. And I want to advertise the question, because if you look at the paper from Eskin's ICM talk in 2010 that has my name on his name on it, we kind of lay down a claim to being able to do something that we then never did. And I can promise you we're now never going to do, but I think someone should do. It's an interesting question, which is, and I'll just give you an example. We make a much more general claim. So here I've talked about Sol-like groups and Carnot-by-Carnot groups, but I want to go to a different kind of example. I want to look at, I'm going to take the Heisenberg group, which I will write in the usual way, X, Y, and Z. And now you can do, you can make, this is a Carnot group. You could put a Carnot automorphism on this thing, but you can also take alpha T from H to H by doing 1, 1, X, Y, Z goes to 1 e to the Tx, 1, 1 e to the minus Ty. And then for that to be group automorphism, Z is fixed. This group is not Sol-like. When I take, I take R semi-direct, this Heisenberg, this is really not Sol-like. What happens? You sort of, if you look at T and X, it looks like a hyperbolic plane. You look at T and Y, it looks like a hyperbolic plane, but these two hyperbolic planes no longer commute. And I'd even be happy to see a good geometric drawing of this space. In the case of Sol, if you look at our papers, we depend a lot on the fact that you can replace a hyperbolic plane by something that looks like a tree. And so you get a picture that looks like, a horospherical product of trees instead of a horospherical product of hyperbolic planes. And really, as we wrote our proof, that's the picture we were thinking in, was about trees and not hyperbolic spaces. It's not an original idea to do that. It's also due to Gromov that you should replace hyperbolic spaces by trees. But here, I don't know what a discrete model of the space is even. Like a nice discrete model of this space, I don't have one. And for me, at least, when you work on quasi-isometries, you want to work with nice discrete models of your continuous spaces because the continuous geometry is irrelevant. And so, the goal, which I actually think is ambitious, is prove conjecture A for this group. Yes.
You can take SL2R semi-direct H, and then you can take SL2Z semi-direct the integer Heisenberg group, and so you have a discrete model of something larger.
But it's not a uniform lattice, so it kind of stinks.
Oh, thank you.
Yeah, no, I mean, I agree that there's something one can try and do there, but it actually runs into trouble. You can build slightly bigger examples where you can build nice discrete models, but then they're bigger examples and they're more confusing for other reasons. I'd really like a discrete model of this one, which is the minimal example of sort of non-Sol-like geometry of a solvable group. This is the smallest non-Sol-like example, and you can hope that this group. Yes, this group has lattices. Just the integer points is a lattice. I'm implicitly writing a rational structure on this group just by how I represent it as matrices and just not just the integer points. Well, yeah, if you just take the integer points and you take any, for the integer point in the r direction, you take any integral hyperbolic matrix, it'll work here just like it works in Sol. And really, one way you can see that is that this group is a central extension of Sol. And you might want to write down a proof that uses this geometry, uses the fact that it's a central extension, but I don't know how to do that. Somehow that gets too far away. Playing with the fact that it's actually a central extension of something you understand gets too far away from the geometry that's useful, at least in anything we've been able to do. And I will say, Eskin, Peng, and I had some ideas for how you can handle groups like this, and then we made the opposite of the mistake we made with Sol. We tried to write things in complete generality rather than writing the first example, and that was a mistake in this case because the complete generality got very much too complicated and sort of overwhelmed us and ended that project. Or rather, maybe we got distracted by other projects. Whatever, something happened. All right, so I have a little time left. Enrico, just so I know, when should I stop? Okay, I'll talk for 5 more minutes. And then, I think I've said everything Tullia absolutely wanted me to say already, so I can just say a few more things. So I'm going to state roughly, and Tullia can state it better, so I don't need to worry too much about how rough my statement is. The Tukia type in our title is about theorems like this. This is a theorem actually due to Tukia. So let gamma act on Sn, where n is greater than or equal to 2, by uniformly quasi-conformal maps. And you need some side condition. I'll give you the sloppy one such that gamma acts co-compactly on distinct triples. And then the action is quasi-conformally conjugate to a conformal action. This is an old theorem of Tukia's from the 80s. Tukia was very much interested in Mostow's proof of Mostow rigidity, where he proved something similar with stronger hypotheses. And Tukia generalized it to this, and actually more generally in a way that Tullia will tell you about in the next hour, I think. And so, this is just some sort of rigidity phenomenon that says, I can have quasi maps and make them not quasi. That's all you need to take away from this if you don't already know it. And then the one other thing I'll do to save Tullia a little time is give you a definition. Because I kept saying, and it's a slightly strange notion, I kept saying quasi-similarity in my talk, and nobody stopped me and said, what the hell is a quasi-similarity? Because quasi-conformal maps, we all know, quasi-isometries, we all know. I don't know that anyone defined quasi-similarity, even in this conference, where many nearby things were talked about. And now I'm trying to find where the definition is in my notes on the page straight in front of me. So definition, and the first part of the definition will look odd. So part 1, let's take lambda to be greater than or equal to 1. c greater than 0, two metric spaces x dx and y dy, and then f from x to y is a lambda c quasi-similarity. This is going to look like many other definitions you've seen before, including this week. If I look at the distance in y between images of, oh, I should give them different names. Let's call them A and B. And it's controlled by the distance in x between A and B on both sides by some factors. And, let me parse this for you quickly. I just wrote down the definition of by Lipschitz, where I did something really odd, which is I split my Lipschitz constant into two pieces. Why would I do such a thing? The reason comes in the second half of the definition. So this is a lambda c quasi-similarity. And then a map from gamma to homeos of some metric space xd is a uniform quasi-similarity action if each gamma and gamma is a quasi-similarity. Oh, I should get my quantifiers right, since this is important for the next talk. If there exists lambda greater than or equal to 1, and for each gamma and gamma, there exists C gamma, such that, give this thing a name, such that phi of gamma is a lambda C gamma quasi-similarity. Did I do that right or backwards? I get confused. I think that's right. Yeah, no, that's right. So what's going on here? If lambda is 1, I've defined similarity, right? I've just defined rescaling by C. And so I want, when lambda is 1, for this to be an action by similarities, but I don't want all my elements in the group to have to rescale by the same amount, because that's just an action by isometries for some homothetic metric, and that's not what you want to think about. You want to be allowed to rescale by different amounts for different group elements, but you also want to only be by Lipschitz and not quite similarity. And so that's what this definition is supposed to encapsulate, is that you have groups acting kind of by similarities up to some fuzz in the rescaling. They rescale where instead of rescaling this annulus to that, and this sphere to this sphere, I rescale this sphere inside of some annulus. And so that's the picture of what's happening in these actions. And I should just say to stop, since I already went over my 5 minutes, that, why quasi-similarities? Well, first, they're what show up here. If you start proving these things, you get quasi-similarities. The other place you get quasi-similarities is, if you look at the action on the boundary of any Heintze group, and you look at the set of quasi-conformal mappings that fix some point at infinity, which conjecturally always happens for most of them, then you get quasi-similarities on the boundary. So like the quasi-similarities are actually, even if you're not interested in the exact question I'm talking about and just interested in homogeneous spaces of negative curvature, quasi-similarities show up there too. So I'll stop there.
Questions? Maybe I will ask a question then. So I'm interested in the situation when you have lattices that are not necessarily co-compact inside a Lie group. Okay,
So let me say one thing to that quickly. It's a theorem, I believe, of Mostow's, that if your Lie group is solvable, maybe it's Auslander. It's Auslander or Mostow. Someone can correct me if they remember that for solvable Lie groups, all the lattices are co-compact. So for this world, they're all co-compact, but you know, so they're not co-compact lattices in the semi-simple world, but they're also in these semi-direct products that Mark and I were arguing about, right? You know, have SL2Z semi-direct Z squared is a non-uniform lattice. And there one should conjecture a stronger form of rigidity, I think, but there are essentially, as far as I know, 0 results.
Okay, thank you very much. Okay, welcome everyone. So the speaker is Tullia Dymarz. She's going to talk about the second part of the talk, Tukia's theorem, not Tullia's theorem, but Tukia's theorem on Carnot-by-Carnot groups.
Thank you, Enrico, and thank you for the invitation to speak here. So I will actually talk about Tukia's theorem in this part of the talk and our generalization. So I left Tukia's theorem on the board as David wrote it. So it concerns groups of uniformly quasi-conformal maps of the sphere, and we can conjugate them, he proves, by a quasi-conformal map into the conformal group. And so our generalization of this will be for Carnot-by-Carnot groups. So let me first write that down, and then I will continue. So, oops. So again, this is joint with Fisher and Xi. And so now, instead of having our group acting on the sphere, our group is going to act on N, which is going to be a Carnot-by-Carnot group, which I won't define again because David defined it for me. In fact, I'm very happy that so many of the previous speakers have defined many of the things I need in this talk. So it's a rarity to give a talk where you don't have to slowly define everything. Okay, so G is going to act on N, a Carnot-by-Carnot group by not quasi-conformal maps, but rather by quasi-similarities. And it turns out in this case, quasi-conformal maps are all quasi-similarities, okay? That is a theorem, but for now I'll just say that G acts by uniform quasi-similarities. Then we can conjugate it by a bi-Lipschitz map. And again, a bi-Lipschitz map is itself a quasi-similarity. Really, the quasi-similarities are by Lipschitz. It only matters when we're talking about uniformity. And this is the terminology that's in the literature, so we've been using it. Then there exists a bi-Lipschitz map such that G conjugated by F actually acts on N by similarities. Now, when I throw around these words, I need a metric on here. And so the metric that I'm using here is what this metric is going to be a homogeneous metric. So let's say any homogeneous metric with respect to this automorphism that N is also equipped with. So again, when I write N Carnot-by-Carnot, there's this extra piece of data, as David said. We have this automorphism, which David was calling alpha, but in our paper, we call it D. So I'm going to use D. And the automorphism of the group is is given by e to the td. Okay, so this is the automorphism of n that makes and this nilpotent group Carnot-by-Carnot, and this d is the derivation that on the W subgroup, the Lie algebra of the W subgroup is just the standard Carnot dilation, and then induces on the quotient Carnot dilation scaled by some factor bigger than 1. Okay, so I should tell you, d-homogeneous just means that if I scale 2 points by this if I scale 2 points in the nilpotent group by these automorphisms, then I am scaling the distance by exactly e to the t. Okay, and there's many of these metrics, and the theorem says that whatever one I start with, I can conjugate to similarities with respect to, again, another d-homogeneous metric. So both of these are going to be d-homogeneous metrics. Oh, so maybe I said any here, so I'll say it here. I should probably put the homogeneity depends on this d. So any this is going to be maximally symmetric. Okay, so we can't conjugate it necessarily into similarities with respect to the original metric, but there is some really maximally symmetric metric that where this does work. And just, so this is the theorem that I hope to sketch a proof of in this talk. And mostly we will be just working with the nilpotent group and what's happening in the nilpotent group. But I will occasionally go back and forth between the quasi-similarity, quasi-conformal world and the quasi-isometry world of the associated Heintze group. So let me just, again, David said this in words, but I'm going to quickly refresh your memories that if I have quasi-isometries of the Heintze group, so this is the Heintze group where the action is by this automorphism defined by this derivation. And actually, this will work for any Heintze group. Quasi-isometries of this correspond to quasi-conformal maps of the boundary. Okay, and the boundary here is just a sphere, which we can identify with n union infinity. And for many of these Heintze groups, all quasi-isometries actually fix a point at infinity. So instead of having to consider quasi-conformal maps, we really just have to look at quasi-similarities of n with respect to, again, some d-homogeneous. This is going to be my d-homogeneous metric. Right, so for example, Tukia's theorem, you can say something about quasi-isometries of hyperbolic n+1 space, and that those are identified with quasi-conformal maps of the boundary sphere. And in that case, this is not true. It's not the same as bi-Lipschitz maps or quasi-similarities of Rn. And in fact, conjecturally, the only places this isn't true is when the Heintze group is isometric to a rank 1 real symmetric space. Okay. So this is, by the way, I should say, if Eve is in the audience, this is Eve's pointed sphere conjecture. So, which is still not completely resolved, but anyway, in our case, it is definitely true that this is equal. And so I will sometimes go back and forth between talking about quasi-similarities or quasi-conformal maps and quasi-isometries of the associated Heintze group here. Okay, so let me give you, what do I want to say now? Okay, maybe I should say a little caveat here. The way I have stated this right here technically only works for dimension of W. So I guess I should say, it's implicit, of course, when I say Carnot-by-Carnot, that it comes with the subgroup where I'm actually doing the Carnot dilation. So the way I've stated this, it's true for dimension W equals to 2. When the dimension equals 1, we actually need an additional condition, which is amenability of the group, which is irrelevant for the quasi-isometric rigidity part because all the groups are amenable. Okay, but as a theorem on its own, we need amenability here. And then in dimension, when the dimension of the quotient is equal to 1, then the proof is slightly different. So maybe for this talk, we'll just assume that the dimension of both of these factors, both W and mod W, is bigger than 2. And the reason for that is that, again, Tukia's theorem actually only works for dimension bigger than or equal to 2. And we heavily use Tukia's theorem basically whenever we can to prove our own theorem. Any questions about this? Yes, I was gonna say that. So so first I will give you like a 2-line proof of Tukia's theorem, which is, really not enough to understand it if you've never seen it. I guess I could do it now since you asked. So right, so this was Tukia's original theorem. It was proved later by, this goes down, unfortunately, okay. Chow for the case where N is Heisenberg group. And then Shangdang Ji noticed that actually Tukia's theorem also goes through when N is Carnot. But again, you have to, the conformal action might not be with respect to the standard metric that you, or with respect to the metric that you started with. It might be a slightly different metric. In fact, he has counterexamples. This is his result, but it is included in our paper because that was a natural place to fit it in. But he observed this. And of course, I should also probably say that, in some of these cases, when these are rank 1 symmetric spaces that are not, where N is not the Heisenberg, let me just put it like this. The Heisenberg group case here, of course, we've seen at this conference, corresponds to complex hyperbolic space, right? The Heisenberg group is the boundary of the complex hyperbolic space. So if you're looking at the boundary of the other rank 1 symmetric spaces, that's Pansu's result that actually all maps are conformal. So you don't even need a Tukia-like theorem to say that, to consider what quasi-conformal groups look like. That answers your question. Okay. Yeah, and I was going to say that, but I'll say that now. So that's kind of the history. So let's now go and take a tiny look at Tukia's theorem. I assume everybody is comfortable with quasi-similarity is just a bi-Lipschitz map, but we're measuring uniformity in a different way. Okay, so for Tukia's, okay, let me thank Luca, who defined quasi-conformality, which means I don't have to. And the nice thing that he pointed out is that there are several definitions. There's like a definition that looks at it's a, a metric definition, an infinitesimal metric definition. So you're just considering the metric, the distance function on your space. There's also sort of a differential perspective where you look at the derivative, which, lucky for us, exists almost everywhere. And then you can consider the derivative and kind of look at the eigenvalues to see how much things stretch. And if they don't stretch too much, you're quasi-conformal. And or if they're not too different from each other, you're quasi-conformal. That's the whole thing, right? So Tukia really uses this differential perspective, and so he's looking at, he's like, okay, these maps are differentiable almost everywhere. So we can define a conformal structure. On Sn, and again, really, you don't have to worry about Sn. You can think of Rn union infinity, but everything is only going to be defined almost everywhere. So let's just forget about that extra point at infinity. This way we just have one chart, and basically it's done in a very sort of differential geometric way, where very similar to a Riemannian metric. So a conformal structure is going to be an assignment of an element here. Okay. But again, so he can't do this everywhere. So this is going to be an assignment almost everywhere. And it's going to be, we just want it to be measurable. Anyway, I don't want to get into too many details. But if you have a quasi-conformal map from Rn to itself, which is the ones that we care about, then you're going to be able to, define a pullback of whatever structure you have. And if your pullback kind of preserves your structure, then you're going to say that F is conformal with respect to mu. And again, like this is, exercise. Every quasi-conformal map has some conformal structure that it's conformal with respect to. That's kind of like, an exercise you might give in a differential geometry class. I won't even write it down to save space. And then the first step of the theorem is to show that all of G there exists a G invariant conformal structure. Okay, and actually this isn't terrible. And again, we want this to be measurable. That takes some work too. So maybe I'll leave this as an exercise too. You're basically using the fact that this is cat 0, if you know what that means. What was I going to say? Oh yeah, and then sort of the standard structure. Usually when we say conformal on Rn, we mean conformal with respect to the standard structure. So mu of x is always the identity, the equivalence class of the identity here. And that's what we usually mean by conformal on Rn. And somehow, what he needs to show is that this invariant conformal structure can be conjugated. So you're invariant with respect to this conformal structure. You would like to be invariant with respect to this one. And so somehow you need to conjugate yourself so that that invariant structure becomes this new one. Okay, again, this is like the shortest proof of Tukia ever. So it probably isn't meaningful if you haven't seen some of this before. But what I just want to emphasize is, it's using this differential notion of quasi-conformality. The final steps is, so find F such that the conjugate of G, so this is going to be quasi-conformal, is has, let's just say, has mu equal to the standard structure, right? So then you're conformal with respect to the standard structure, so you're conformal. And the way you do it in dimension n equals 2 is basically you can pull back any, yeah? Oh, sorry. Have I skipped? Sorry. Yeah. Did I use, oh, because David wrote it, that's why. I kept David's, thank you, Shangdong. Okay, yes, my groups were gamma. Sorry, guys. This is, it's okay. They're friends. Okay, now I guess I'm gonna have to stick with gamma since I stuck with that. Okay, so when n equals 2, you can basically just pull back the structure, and this was already done by Sullivan. When n equals 3, Tukia needs an extra condition, and in our statements, yeah, I guess I've already erased this, but in our statements, oh, did I not add it in my statement? I just erased my theorem. I just realized I don't think I added it. I was too busy with, okay. Did you add co-compact Leon triples? Yes, you did. Okay. So my statement should have also had co-compact Leon triples, okay? It was really meant to look exactly like Tukia's theorem, except quasi-conformal replaced with quasi-similarity, and SN replaced with Carnot-by-Carnot. So please add that to your statement. We do need that because, like I said, our theorem follows Tukia's a lot. So actually, for n equals 3, what you need is, and what co-compact Leon triples gives you is radial points. So radial points are, if this is n, well, in our case, it's Rn, but it will soon be n, is simply a point and a sequence in my group. So I have a sequence inside, I guess, gamma. I can still call them G's though, such that for any geodesic that ends at my point, okay, this is a definition most people have seen, there is some constant C such that okay, for any point there's a constant C such that if I look at what GI does that to that point, it converges to X. And he needs that this radial point, so this is a radial point. He needs that mu, let me call this X naught. Mu is approximately continuous at this radial point. And Pierre Pansu defined this, so I don't have to. But it doesn't matter because I'm just giving a rough sketch. So why am I bringing all this in? I want to tell you how this map is constructed. It turns out this map is constructed as a limit of these guys composed with scaling factors, where I can view these as isometries. If I'm looking at, so lambda GI is basically going to take wherever GI sent this point right here and map it back here. Okay, so if it sends it down here, the isometry will pull it to close to this point. Okay, and that will give us convergence here. So sorry, this should be a limit of these isometries composed with these quasi-isometries. Remember I said I'd go back and forth between viewing things on the boundary and inside the space. with one additional thing. Why is this mu important? We're going to actually also conjugate sort of by an affine map on the boundary that's determined by this, the structure here. Okay, that was probably too little and too much at the same time, but if you want a slightly better explanation of this, Bourdon has some lovely notes on a mini course he gave many years ago summarizing Tukia's proof. And but the point was really the construction of this conjugating map is you're composing these group elements with boundary maps of isometries of your space. Okay. All right, so I would ask any questions, but maybe I won't because there's obviously many details have been omitted and I'm just giving a flavor of what's going on. Oh, I guess I should say this is where co-compactly, the existence of this radial point is where co-compactly on triples is important, because then almost every point is a radial point, okay? And that's why often in the statements you just say, oh, I act co-compactly on triples. The quasi-isometric version of that is I'm quasi-isometric to the space, or I act by quasi-act co-boundedly. So there's various conditions that will give you a radial point that you can ensure your map, your conformal structure is approximately continuous at. Okay, but if you look at the proof, it's really all is needed is a single radial point where this is approximately continuous. And you can kind of blow it up. And there's a lot of like measure theory ensuring that the convergence of these maps, which are quasi-conformal, do converge to something that's quasi-conformal and actually quasi-conformal with respect to the standard structure. Okay. Okay, so now I want to move into the world of how this applies to Carnot-by-Carnot. And again, I'm going to do it by looking at the simplest example that David gave, and that is when n is Rn plus m. Okay, he said 2, but again, I'm assuming my dimensions are always bigger than 2, so I've decided to use Rn plus m. In this case, my W will just be Rn, and then my n mod W will be Rm. And of course, I should give you the derivation that defines my automorphism on R that's making this into a Carnot-by-Carnot group. And that's just, I'm going to say 1 times the identity on Rn and 2 times the identity on Rm. So this is my derivation. It's a Carnot-by-Carnot group. Oh, I should give you a d-homogeneous metric. And David didn't give you this, but that's okay because I'm going to. I didn't say he had to. So d-homogeneous metric on this can be given just by the max of the change in x values and the change in y values to the 1/2. So here I'm writing, elements in here are x, y, where x is in Rn and y is in Rm. So this is a d-homogeneous metric. You can plug in the e to the td and see that it transforms exactly how you'd want it. You're scaling either this by e to the t, which pulls out, or this by e to the 2t, which you take a square root of, and it also pulls out as e to the t. So this is indeed a d-homogeneous metric. And so now, in order to be able to sort of understand quasi-similarities, i.e. by Lipschitz maps, with respect to this metric, we want to see what kind of structure they have. So it's actually not hard in this case to figure out that any by Lipschitz map has the following form. It splits as a map. The first coordinate depends on both coordinates, and the second only depends on the second coordinate. Okay, so any bi-Lipschitz map actually preserves cosets of W, which in this case is Rn. This actually holds for all Carnot-by-Carnot groups. Any bi-Lipschitz map of a Carnot-by-Carnot group will preserve cosets of W. Okay, and because it preserves cosets of W, we also get induces bi-Lipschitz map of the quotient and mod W with respect to sort of the metric, the Carnot, well, okay. In this case, it induces maps on here. And if we just square this, you will get the standard metric on, I guess, Rm. Okay, so it's going to, up to snowflaking, you're going to get let me write it like this. You're going to get an induced metric on the quotient that came from the original one defined by the derivation. With the proper snowflaking, you will get, so I guess I should say this should be, well, okay. I'll leave it like this, okay. Okay, so it has this structure. Oh, I've already said, so I said a little too much. Induces a map. It will indeed be bi-Lipschitz once you snowflake it. So this thing actually ends up being bi-Lipschitz with respect to Y. Yeah. Here, this map ends up being bi-Lipschitz with respect to X. Okay, so that means along the W coset, okay, it's the map from a coset to coset is bi-Lipschitz in X, okay? And however, it's only 1/2 Holder in the Y direction, okay? So from this, you can see, if we want to apply Tukia, we can do it to maps that are differentiable almost everywhere. So we can, for example, apply Tukia to the quotient. And then, oh, nobody's used color chalk yet. We can apply Tukia to the quotient, so we can kind of fix this to get a similarity after conjugation. Okay. And for this map right here, well, we can't do anything in the Y direction because it's not differentiable in that direction. So instead, what we do is, and like David said, this was really part of my thesis, which was a while ago. We define a foliated conformal structure. So again, it's an almost everywhere on Rn plus M, except instead of having the structure defined, of dimension n plus m, it's only of dimension n because it's only in the direction of in the x direction. Okay. So again, the moral is we can use Tukia whenever things are differentiable, and we do. Okay. So once we apply Tukia in these differentiable directions, I will write down what the map looks like. So anytime I say apply Tukia, That means we're going from something that's quasi-conformal to conformal, or quasi-similarity to similarity. So well, again, in this case, things are going. If I just do Tukia on the quotient and Tukia along each fiber, then let me show you what I get. So now my map is a similar. So let's see, it's a similarity in this constant. A similarity of Rn is something like, I need a new, like something like this, right? It's an affine map. It's an affine map. That's also a similarity. Okay, so this is like rotation plus dilation, okay? That's what happened here. I'm a similarity, no longer just by Lipschitz. And here, I'm also a similarity. So I'm gonna call this something like this, except things depend on y now, because, that dependence of y doesn't go away. So this depends on y, this depends on y, the translation constant depends on y, okay? Because I only have this foliated version. It turns out it's pretty easy to get rid of this dependence on y. Okay, that's just some arguing about, hey, I have a uniform group and I can't be rotating in different ways on different pieces. I can't be stretching differently on different pieces on different cosets. But basically the end of my thesis was up to a similarity, I got something like this. So I've kind of, oh yeah, the other thing is there's some compatibility issues between A and B that I have to worry about. Like maybe I'm not stretching in the appropriate ways on A and B, and so it's not a similarity of the whole space, right? So, but in this case, the compatibility worked out well, and I was only left with something like this. And this was enough to deal with, actually it was enough to deal with quasi-asymmetric rigidity in some roundabout way. But later, so maybe I should say this was eventually published in 2010. But later, I started working with Shandong to try to get rid of this right here, okay? And it turns out that, and maybe, okay, up to similarity, I can assume that my map looks like this. Again, and I can assume that this is 0. And the other condition is that came from already up here is that this map is 1/2 Holder, right? So this map is 1/2 Holder. And so I actually can look at the space of all, oh no, I've already used B. Oh, okay, I'll call it script H, even though that's definitely not what we call it in the paper. What do we call it? I think we call it E. E. Okay, good. Another new one. If you look at the set of all maps, I guess, so this would be a map from Rn. So that's Rm to, this is now to W, which is Rn, okay, such that this is 0 and S is 1/2 Holder. This guy right here is a locally convex topological vector space. And it turns out that G has a nice action on a convex compact subset of this locally convex topological vector space. And with the additional assumption of amenability, which we had in our case when we were considering quasi-isometry, this Day's theorem now ensures that if you have a setup like this, then you have a fixed point. Okay, so this is And I don't have time to convince you that having fixed points is good because it allows you to conjugate things away. But that is exactly what we do, is we can use this fixed point to conjugate this extraneous sort of shearing bit. I should put the word shearing away from our group. Okay, so after this was, I guess, published in 2016, and it's with G. But after this this work, we now no longer had shearing. We did have to assume G was amenable, but I'll leave it like that for now. Okay, so I've tried to, let me see how much time I have. How much time do I have? Like 5 minutes, 6 minutes? Okay. Okay, so so now we had this ambitious goal of trying to do the same thing for nilpotent groups with expanding or contracting derivations, depending on which way you're viewing these things, right? So basically, boundaries of Heintze groups is what we were trying to look at. And so what we could do, what we ended up being able to do in general is, you know what? I don't have time to talk about in general. Basically, in general, it didn't work. So we were quickly forced to consider the next best thing, which is, let me call this general Carnot-by-Carnot. No, the truth is some bits still do work in generality, and one of our papers does deal with a sort of general case. So I've already mentioned some of the elements here. So again, Carnot-by-Carnot, I have this this subgroup here, W, and you know, my derivation. Let me also give you a caveat at this point. I am always going to, I'm going to go back and forth between talking about identifying the Lie group with its Lie algebra, because a lot of things make more sense to say on the Lie algebra level. Okay, and I will sometimes forget to use this nice frac notation when I say it. So assume these are either Lie groups or Lie algebras, and of course the coordinates we use come from the Lie algebra. So okay, so again, the setting is I have this group acting on N by quasi-similarities. And just like before, we want to know what the structure looks like. W is preserved. So any element, actually any bi-Lipschitz map preserves cosets of W. Okay, so what that means is it sends, you know, the coset PW to GPW, right? Okay. You know, and so this is one family of maps we're going to study, but also because it preserves it, we have an induced action on N mod W with respect to, again, like I said, some metric determined by, like it's actually a Carnot-Cartesian metric on this quotient group, which is a Carnot group that's being scaled by a Carnot dilation times some alpha. Okay, so we can actually do Tukia on here. Okay, so again, what I mean by do Tukia is do one of these generalizations, which I now erased, of Tukia's theorem to Carnot groups. Okay, and so I can assume that G acts by similarities. Okay. It turns out I can also, maybe I'll move this back here. I can also do a version of foliated Tukia. So that this map that, and already here, the notation gets to be a nightmare. In order to really get this to be a map of W, I should instead consider the map. Maybe I will use a different color here. Or maybe I'll move it down here. To get a map of W, I'm going to consider the following map. So this is now a map of W, and this is now, again, going to be, after doing foliated Tukia, I get, this map is an automorphism of W that depends on P, just like before, right? My original similarity, okay, again, it's also a similarity, but it's going to depend on Y here, okay? And the hard part is exactly this part that I said was not too hard, removing these conditions on Y. In some cases, this ends up being even impossible. We just have to work with it. And then applying Day's theorem will work in certain conditions, but not in all conditions. How much time do I have? Couple minutes? Okay, let me just say, okay, maybe I should have skipped Tukia's theorem. So, as David said in the last talk, actually Carnot-by-Carnot groups are pretty complicated. And if we look at the Lie algebras of n and decompose it with respect to their eigenvalues, and W also we can decompose as a Carnot group. Now as a Carnot group, again, with respect to the eigenvalues of D, which we assume the lowest eigenvalue is always 1. And now the thing with, now if n is a product, so if n is actually a product with some other group H here, then actually everything works out as intended. The complicated part comes that in a Lie algebra sense, we can always come up with a transversal to W inside here. But there's just a lot that can go on. So let me tell you what we do know. So okay, so the first eigenvalue is always going to be 1. Okay, but I'm trying to see. But at some point, we're going to get to V alpha. So alpha, I'm going to call I'm going to assume my derivation is on W is just, you know, lowest eigenvalue 1 and then integral eigenvalues above that, right? And the induced map on the quotient, the derivation is going to look like alpha times something like this, okay? And so at some point, this alpha may coincide with one of these. So at some V alpha, I'm going to have components of both showing up. So I will have W alpha and a piece of this H. And I'm going to call this H1 because when I'm dealing with a quotient, I can just rescale everything and assume that I have a regular Carnot scaling here. This is kind of the first layer of this is the component that is in correspondence with the first layer of this derivation of this Carnot group here. And again, since I really don't have any time left, if alpha is, so here, here, if alpha, notice that the eigenvalues here are all integers. So if alpha is not an integer, this part disappears. And all I have is components that came from here, okay? It turns out in this case, algebraically, you can show that you're actually just a central product and things are a lot easier. Also, if alpha is irrational, you can even show that you're actually a direct product. Okay, that's not hard. The really hard part where most of our paper comes in is when alpha is an integer and we have this non-trivial components from both the W and the H coming in here. So most of the paper is this work. And it's really trying to understand what do these maps look like. You get similar kind of phenomena where you get these similarities that are automorphisms, you get shear maps, but the non-commutativity and just makes everything much, much more difficult. So I don't have more time to say anything more than that, but I'll just feel free to ask me or Shangdong or David if you want the specifics of what happens here. So.
Are there any questions for Tullia?
If it's not too complicated, can you write down what the convex compact set looks like on the upper blackboard on the left?
Write down what it looks like?
No. Yeah, what is this convex compact?
Oh, this one? Okay, so basically this is going to come from the elements. So for each element in this group, you're going to have one of these guys. Okay. It's just going to be that the convex closure or something of that. That's it.
Oh, okay.
Yeah.
Okay. No, because I'm sure you thought about it, but there are also some more general fixed point theorems where you don't need to assume G amenable, but you need to assume the action to be distal, which essentially says that's the real Narzewski thing, that distal means that if you have 2 points, x different from y, and you look at their diagonal G orbit, then it stays away from the diagonal. So, and then you have a fixed point. Anyway.
Let me also say that in this later work, we have a way of getting around this, and we don't have to assume amenability in that case.
Are there other questions? Okay, if not, let's thank Tullia again and let's go for lunch. So I remind you that so the people that are speakers or are financially supported, they should have received a ticket to go for lunch in the cafeteria of the university, not the one of the Scuola Normale. So we're going there, and the other one are free to go everywhere.
Okay, so welcome back to this afternoon session. So the next speaker is Pierre Pansu of Paris-Orsay, and he will be talking about quasi-conformal classification of 3D contact Lie groups.
Thank you. Thank you for being here. So I'm about to tell you the story of a disaster. So yes, the main results I wanted to explain, I realized during Tullia's talk this morning that there was a mistake on it. So please don't pay attention. So we are dealing with quasi-conformal mappings. They've been introduced already. So what I've wrote has already been illustrated by the following picture. So we consider map between metric spaces with the following property. Spheres are mapped to slightly distorted spheres, slightly in the sense that here the out radius, the radius of the largest ball containing the image, and the in radius, the radius of the largest ball, which is inside, the ratio is uniformly bounded. But now I will study this kind of maps in the context of sub-riemannian or sub-Finsler metrics in 3 dimensions. So where the distribution is a contact structure. So now I will consider Lie groups with invariant contact structures. So this data of the group and the contact structure, I call this a contact Lie group, just for this lecture. And now I observe that choosing an arbitrary sub-Finsler matrix, which are left invariant, give rise to, by Lipschitz equivalent metric spaces, in particular quasi-conformally equivalent metric spaces. So the problem of classification up to quasi-conformal equivalence makes sense for contact Lie groups without specifying a metric, an adapted metric. So now here is the statement I plan to explain. So here we deal with all 3-dimensional Lie group equipped with a left invariant contact structure. So the first 2 items are disastrous. I don't know what the answer is. So the first one says that for the group PSL2R, there are 2 left invariant contact structures, family of contact structures, and possibly 2 different equivalence classes. And this I don't know, and I don't really make a bet, in fact, whether they are quasi-conformally equivalent or not, or they eventually become quasi-conformally equivalent by taking finite covers or infinite covers. This I don't know. And until this morning, until I started hearing you speak, Tullia, I thought I was able to show that 2 other contact Lie groups were not quasi-conformally equivalent. This is here mod R2 is this group of motions of the Euclidean plane, and consider its universal covering space, and which is diffeomorphic to R3, and Heisenberg group. Yes? That to this effect? Ah. Exactly to that effect? Good, we saved. Well, go. Go ahead, yeah. But then you can continue. I'm sorry, I completely overlooked this work of yours and Catherine. Do you want to give the okay. Then there is an easy observation that 2 non-isomorphic groups give rise to the same quasi-conformal equivalence class. And then in all other cases, quasi-conformal equivalence implies isomorphism. So I must say, I don't think that the little which is known here reflects what should happen in higher dimensions. It's simply there are so few possibilities in 3 dimensions that it's hard to believe that the situation should not be more complicated. And I'll also observe that all the contact structures that show up, they are all diffeomorphic. So this statement has nothing to see with contact topology. Too bad. So maybe I will go a bit fast through the first easy remarks. So first, which Lie groups in 3 dimensions admit left invariant contact structures? That's a very easy exercise. And in fact, all but 2 of them. So the abelian group, clearly all invariant 1 forms are closed. And the group of translations and dilations of the plane. This is less obvious, but the computation shows this. So the next step is to see whether a given Lie group can have different left invariant contact structures. And here again, the answer is easy. So it's just a matter of connected components in the set of left invariant 1 forms. So indeed, it's a classical principle, at least that on compact manifolds, when you continuously deform contact structures, they stay diffeomorphic to each other. So there is an equivariant version of that theorem that applies here. And so now we need to understand the set of invariant 1 forms. And the condition for contactness is a psi wedge exterior differential of psi non-zero, right? And this is quadratic. So and also 2 forms which are proportional give the same contact structure. So the invariant 1 forms form a vector space, a 3-dimensional vector space. So up to rescaling, this is a 2-dimensional projective space. And the non-contact ones, they consist of a conic, eventually degenerate in that projective space. So you have a small number of connected components, at most 4. And now up to automorphisms, going through the classification case by case shows that there is in fact only 1 class except for PSL2R. And so on PSL2R, the invariant contact structures are more or less obvious. You can view PSL2R as acting on hyperbolic plane, and it acts transitively, in fact, simply transitively on unit tangent vectors. So you can think of PSL2R as a unit tangent bundle or cotangent bundle of a hyperbolic plane. And as such, it carries a tautological contact structure. And another point of view is to, again, from this action of PSL2R by isometries on hyperbolic plane, you can view the group as a circle bundle over hyperbolic plane and pick a connection. And such connections have to be a contact because the curvature of hyperbolic plane is non-zero. And this represents the two connected components. But I don't know whether they are isomorphic as they're bi-Lipschitz or even quasi-conformal or not. They define opposite orientations, but this is not sufficient to exclude a quasi-conformal mapping, mapping one to the other. And then last easy remark is that this group, which you can view as acting on, so this group here is a subgroup of PSL2R that acts simply transitively on hyperbolic plane. And so the product group acts simply transitively on the total space of any circle bundle over hyperbolic plane. So on PSL2R in particular. And this gives the quasi-conformal mapping, in fact, an isometry for suitable sub-riemannian metrics. So here are the easy remarks. And now we start entering the subject. So our main tool will be the following fact, that if the isoperimetric dimension of a manifold is large enough, so in this case, larger than the Hausdorff dimension of Heisenberg group in its sub-riemannian matrix, then any quasi-conformal map is a quasi-isometry. So where does this come from? So it's an old story. In fact, when Gruetzner defined the word quasi-conformal in 1928, in fact, his first theorem was more or less of that nature. So he dealt with global quasi-conformal mappings of Euclidean plane, and he proved some distance estimates. He showed that these maps are not always Lipschitz, but always Hölder continuous in a precise manner. In fact, they're quasi-symmetric. And later on, Teichmüller studied the same question in the disk or for hyperbolic plane. And Teichmüller showed, more or less by the same method, that quasi-conformal mappings of hyperbolic planes are quasi-isometries. So they are kind of Lipschitz at large scales, but at small scales, they are no better than quasi-symmetric. So Hölder continuous, but a little bit better, but no better. And later, much more recently, Jacqueline Ferrand studied this kind of problems for general Riemannian manifolds and extracted the geometric input needed. And it has to do with isoperimetry. So I have not defined isoperimetric dimension. What I mean by an isoperimetric inequality is a relation between volumes of domains and areas of their boundaries. Volume of some domain is controlled, or rather, well, let's write it this way. Area of the boundary is at least some function of the volume of the domain up to some constant. And the dimension, I will put it here, d minus 1 over d. So if such an inequality holds for all domains, then I say that the space has isoperimetric dimension at least d. And soon I will describe examples. So what are the isoperimetric dimensions of contact Lie groups? So then, so here we have a piece of the list of contact Lie groups. So for the compact ones, the isoperimetric dimension is 0. Then for groups which are quasi-isometric to Euclidean plane, like the Euclidean motion of the plane and the quotient of Heisenberg group by a cyclic subgroup of the center, then the isoperimetric dimension is 2. Isoperimetric dimension is a quasi-isometric invariant. for the universal cover of this group, which is quasi-isometric to Euclidean 3 space, isoperimetric dimension is 3. For Heisenberg group, isoperimetric dimension is 4. And otherwise, it's strictly bigger than 4. Then it's infinite, in fact, in all examples. So how can this be computed? Simply because isoperimetric dimension controls volume growth. And so now, once you know a Lie group has polynomial growth, some old results by Dymarz gives the structure of such groups. They're essentially nilpotent groups and solvable groups obtained by extending them with weights which are pure imaginary. So it's easy, at least in 3 dimensions, to go through and establish this list. Right. So these will be the difficult examples, because for all others 3D contact Lie groups, we will be able to use this principle, and the classification boils down to the quasi-isometric classification, which has been known for some time. Here it is. So usually, in fact, here we see the principle of Cornelier working. You remember that explained to us that every Lie group has a model which is triangulable, and then we expect triangulable Lie groups to be quasi-isometric if and only if they are isometric. We expect, and we know it in 3 dimensions. So that's when I'll go through the details of this. So here are the groups for which the triangulable model is not obvious, is not the group itself. So the universal cover of the motion group of the plane, sometimes called the roto-translation group, is quasi-isometric to, in fact, isometric for a suitable metric to Euclidean 3 space. So when you pass to quotients, you get spaces which are quasi-isometric to Euclidean plane. And the same holds for quotients of Heisenberg group. Now, the universal covering space of SL2R is quasi-isometric to this product. We've just seen that they're quasi-conformal, and so the principle QC implies QI applies in this example, but this can be seen directly. And then again, when you take quotients of these, you obtain spaces quasi-isometric to hyperbolic plane. So they are all quasi-isometric. And what about the others? We can use isoperimetry. The isoperimetric dimension gives us the 4 classes that were on the previous slides. And then the solvable unimodular group has a special typically solvable isoperimetric behavior. Its isoperimetric inequality is not quite linear. And the other ones have a linear isoperimetric inequality. So this allows to sort up to quasi-isometry among already rather thoroughly, but not completely. So some further arguments are required. So for instance, dimensions of asymptotic cones. You remember Cornelius' talk. He understands the dimension in all cases. And so we see that for this group, the dimension is 2, because this is hyperbolic plane, whose asymptotic cone is 1-dimensional times R, makes it 2-dimensional. And this one is quasi-isometric to it. But it's strictly less than, well, it's 1 or 0 for all other examples. So this allows to put these two examples aside, which are in fact only one quasi-isometric class. Then, so what are the other groups like? They are solvable groups, which are extensions of R2 by R with various kinds of one parameter groups of automorphisms, matrices. And so among them, there are the contracting automorphisms, which give rise to Heintze groups, negatively curved groups. And then one can use the theory, the hyperbolic theory, and use invariance like the dimension of the ideal boundary, and further rigidity, further invariance like LP cohomology, to distinguish among all these negatively curved groups. And what does remain is there remains for instance, the semi-direct products R2, wait, this way, right? Given by matrices which are diagonal, but with two different eigenvalues of different signs. And if mu equals 1, we get so on the one hand. And when mu is between 0 and 1, we get this one parameter family of groups which are not pairwise isomorphic and which are not pairwise quasi-isometric either. And I think it seems to me that's a result by David, Fisher, and various co-authors. Is he around? No. Yes, help me. This, well, yes, no, there is no. They're not so easy to handle. Right. So it seems to me, so, you know, when in any classification work, there is always a mistake. I don't know of any important, but this one, classification where when first published, there wasn't missing examples or isomorphic things which had not been seen. So I'm not 100% certain that I miss things, even in this very, very easy context. Right. So this deals with examples with isoperimetric dimension bigger than 4. So next, we need to show that the examples with isoperimetric dimension less than or equal to 4 are not quasi-conformal to these ones. And this does not follow from the general principle. But fortunately, there is a conformal invariance that will distinguish them. It's parabolicity, conformal parabolicity. So you say a manifold, well, it's a concept from Riemannian geometry, which is simply adapted here to sub-Riemannian geometry. So conformal parabolic means if you fix some open set, bounded, then you can find smooth functions which are take value bigger than 1 on that set, and such that the L4 norm of the gradient can be made arbitrarily small. So why L4 norm? Because that's the norm which is naturally conformally invariant. Conformally invariant for contact sub-Riemannian matrix or sub-Finsler matrix. Right. So this is indeed a quasi-conformal invariant. So it's obvious for smooth quasi-conformal mappings, but the argument goes through for homeomorphisms. This has been known in Riemannian geometry or in analysis since Grotsch nearly. And this is not too hard. So now, which of these 3D contact Lie groups are conformally parabolic, answer exactly the list I gave before, exactly those of isoperimetric dimension less than 4. Why? Because isoperimetric dimension controls conformal parabolicity or the opposite, which is hyperbolicity. Right. So good. This means that this small family of spaces, of difficult spaces, we know now cannot be quasi-conformally equivalent to any of the previous ones, the ones that we have already classified. So what does remain? So in this class, this small family, in fact, just by topology, you see, SU2 is a 3-sphere, SO3 is a real projective space. They are not homeomorphic, so they're not quasi-conformally equivalent either. And the same for the others. So the quotients of these two groups are homeomorphic to a circle times a plane. And these are homeomorphic to R3. So these certainly are not pairwise quasi-conformally equivalent. And now imagine we can show that the simply connected examples are not quasi-conformally equivalent. Then a fortiori, the quotients won't be either, because we're dealing here with homeomorphisms which lift through coverings. So there remains this question of comparing this group and this group, and then I can tell you the good news. It's a theorem by Enrico Ledone, Catherine Fessler, and Pekka Koskela that these two examples are not quasi-conformally equivalent. And this, well, I could finish the lecture here, but instead I will explain to you how I tried to and failed to prove that theorem. Just for distraction. So parabolicity, this weird notion where you try to minimize the L4 norm of gradient of functions which are normalized to be bigger than 1 on an open set. Well, what does this mean? So let's do this first in a Riemannian setting in dimension n. So again, I fix some open set, bounded open set, a ball, let's say. Then this produces a relative cohomology class in degree 1. The cohomology class represented by the differentials of these functions, which are constant on B, and we have compact support. So, and now we're minimizing the L here. The Ln norm of gradient is something very natural. It's defining the norm of that cohomology class, right? And so conformal parabolicity amounts to saying that a certain homology class has a vanishing norm, Ln norm. So now I'd like to play the same game, but with cohomology or differential forms of higher degree. And so indeed, at least one can make definitions. And so in Riemannian geometry, definition already exists of the conformal cohomology. It's the cohomology of the Durham complex, a bit as we did here, with LP norms, but we choose the exponent P in order that the norm be conformal equivalent in each degree. So in a Riemannian case, for K form, the exponent should be n over K in order to be a conformally equivalent, invariant. And you can form a complex of Banach spaces in this manner and introduce its cohomology. And indeed, what I described here is very close to dealing with the L infinity n cohomology. Here, when k equals 0, you should put infinity here. But as you may guess, this may cause troubles, and indeed doesn't quite work. In fact, L infinity n cohomology is never 0, just for local reasons. Even just in a ball, there exist functions with whose ln norm of gradient, smooth functions, whose ln norm of gradient is arbitrarily small, but which take value 1 at the origin. It's easy to make examples from simply the log of the distance to the origin. And again, what is hidden here is a conformal invariance. So this is always non-zero. So, but if you manage to avoid these local phenomena, for instance, by discretizing the picture, then parabolicity exactly boils down to studying the conformal cohomology in degree 1. I'd like to do the same in higher dimensions, but in a sub-Riemannian setting. So what will be the change? We need to find the conformally invariant exponents. So here we're in dimension 3, but beware that we're in sub-Riemannian geometry. In contact sub-Riemannian geometry in dimension 3 has Hausdorff dimension 4. So the numerator has to be 4. And in the denominator, you must put the relevant dimension for an exponent for each dimension. So we know that in contact sub-Riemannian geometry in three dimensions, curves have to have dimension 1, the horizontal curves, but surfaces must have dimension 2, and the whole space has dimension 4. So this alpha of k is not simply k, it changes. And now, but now, even with these choices of exponents, the de Rham complex is not conformally invariant. In fact, the ordinary Riemannian norm would not do. Even sub-Riemannian norm of a form would not do unless you choose differential forms adapted to the contact structure. And this is exactly what the Riemann complex does. So it's a sub-complex of differential forms, which is designed so that two forms indeed are homogeneous of degree 3. And the differentials in a Riemann complex are constructed from the de Rham differential, but are slightly modified. I won't say anymore. I will stick to. It would be very long to explain exactly Riemann's complex. So I hope you'll accept we go to the next step. And the next step is to understand why this Riemann conformal cohomology is a quasi-conformal invariant. So we'll use the following results. First, that when the inverse of a quasi-conformal homeomorphism is quasi-conformal. And then quasi-conformal homeomorphisms are, by definition, they're W14 in 3 dimensions. But in fact, they're a little bit better. This is a classical result in Riemannian geometry due to Gehring. And that works also in sub-Riemannian geometry. Has been done by Henon and Koskela. But now, how does such maps interfere with Riemann's complex? And it's a highly non-trivial fact that these maps, W1P maps with P bigger than 4, induce chain maps on Riemann's complex. I will merely say one sentence. So Riemann's form, in fact, can be viewed as a quotient of the differential forms in low degrees. So one needs show that pulled back by these maps, which are not very regular, but still differentiable, they pass to quotient. But also, when I say they are differentiable in the sense, in the Carnot sense. So there really is something that has to be proven here, and this was done by Kleiner, Müller, and Shandong-Xie not so long ago. Very thankful to them for doing this analytic work. So this implies that quasi-conformal mappings induce chain maps, and so isomorphisms in cohomology, in the Riemann cohomology. So precisely on this Riemann conformal cohomology. So that's more like an analytic point, but a serious analytic point. Now we need to compute this conformal cohomology for the examples at hand. So you remember the examples are the universal cover of the motion group of Euclidean plane and Heisenberg group. So until this morning, I thought I could prove they had different conformal cohomologies in degree 2. And then only recently, I realized I had made a mistake. And you'll see where. So first, let's start with what is correct. So first, the local exactness of Riemann's complex. So in a smooth setting, this is necessary to say that Riemann's complex computes cohomology as usual, the usual cohomology. But here, it's a statement that comes with estimates that says that a closed form in LP admits a primitive, which is in LQ for suitable P and Q. I didn't write exactly the exact conditions which are necessary here. And so that's a local statement. And it fails in a few cases. And I mean, it definitely fails. So we know exactly, we give a complete answer. So a consequence of this is that one can discretize this cohomology theory more or less in the usual manner, using Lerais acyclic theorem, acyclicity theorem. So, and one can show that this LQP cohomology can be computed by using a covering, and it becomes a cohomological invariant of the nerve of this covering, which is a simplicial complex, which is quasi-isometric to the manifold we started with. So I use a different notation. So the LQP here is the Riemann thing, kind of analytic, and the other LQP means the the one which is defined by means of triangulations or approximations by simplicial complexes, and the one which by construction is a quasi-isometry invariant under suitable assumptions. Right. So this works because the exceptions, well, precisely conformal cohomology hits the exceptional cases in degree 0 and in top degree, which is not by chance either, but at least we can use other degrees. Now, and next we must go through computations. So now here is the calculation of the LQP cohomology of Euclidean n space. So if you write here an equality, what you get is exactly the condition for Sobolev inequality for compactly supported functions. It also works for forms. And so you're not surprised to see that there is a connection with the problem of deciding whether a closed LP form has a primitive in LQ. And so this would be for the equality case. And then the inequality follows because we are dealing with this quasi-isometry invariant things, which is defined on simplicial complexes, on discrete data. And then if it works for one value of, well, if LQP cohomology vanishes for one value of Q, it automatically vanishes for all larger values, whence the condition being given by an inequality. And again, there are a few sporadic exceptions where the theorem really fails. Where we know the answer, but the answer is not the one, not the same. And how about Heisenberg group? So that's also included in this joint work. The answer is more or less, it looks the same, except that the numerology is not exactly the same. So you're not surprised to see that the 1 over n being replaced by 1 over 4. And except in degree 2, where it's, why is it 1/2? Because it's the degree where which receives a differential in Riemann's complex, which is a differential operator of order 2. So, well, it's not very enlightening, but this is the answer. So now we're in good shape because the examples we're interested in, the motion group of R2 with universal cover, we know it's quasi-isometric to Euclidean 3 space, and we know that this LQP cohomology is a quasi-isometry invariant. So the theorem applies and tells us that the conformal cohomology in degree 2, so L4 4/3. Sorry, I'm here. Since well, it's bigger than 1. Well, since the condition is satisfied, this cohomology vanishes for that motion group of R2 universal cover. Now, what about Heisenberg group? We also had the answer, and it vanishes again. So I'm stuck. I had made a stupid mistake in these integer numbers, and I realized only this morning that it did fail. So the argument just doesn't work. I don't know. I don't see. So clearly the picture is different between these two examples, Heisenberg and motion group, since we see that the value we reach is really a limiting value in one case and not at all in the other. So maybe there is a way to a bit of room to cure this failing argument. But I prefer to leave the stage to Enrico with his own proof of that theorem. Could you tell us in a few words? No, okay. You don't have to. You don't have to.
But let me ask you a question, because at least there is something that we had to use that I didn't see how you were using it here. So where are you using the local geometry of the roto translation group? So, like where are you using that you're studying, that you're using the sub-riemannian geometry of the roto translation and not just any metric that is quasi-isometric to the Euclidean? because for us was important that the two spaces, Heisenberg group and roto translation, locally at the same dimension, was dimension 4.
Yes.
So there were 2 4 regular spaces. And then in the large scale, one was at dimension 4 and the other one at dimension 3.
Yes.
And you're using the large scale geometry,
Yes.
but I'm not seeing where you were using the local geometry.
I'm using the fact that that exactly is this, these exponents give a conformal invariant. If I would use Riemannian matrix, the exponents would be different. It would be 3 and 3/2.
You're pointing at the Heisenberg group.
I would conclude successive with success, right? But with these values, well,
you were pointing at the Heisenberg group.
so
So
yes.
you just consider the same number, 4
So
and 4/3?
because we are playing with the sub-riemannian geometry, contact sub-riemannian geometry in dimension 3, the exponents I'm allowed to use for conformal invariance are restricted. I have.
So our proof more or less was going like this. So actually one should also try to rephrase what we have done using capacity.
Yes.
Which is some other way of
so this means that you're dealing with one cohomogene degree 1.
Yes.
Right?
So our result was true for metric spaces. So we had 2 metric spaces that had the same, that they were, whose geometry was locally Q bounded, and here is 4, Q is equal to 4. And one space like the Heisenberg group is also a Lovner space, like a satisfy Poincare inequality.
Yes. Yes.
And okay, so it's a proper space. And then the other one, the only important things we were using was, first is that the large scale geometry was strictly less than the house of dimensions.
Yes.
Right? And also that you had an infinite geodesic, but you actually even a continuous quasi geodesic is enough. Yes. So you have this infinite geodesic in the roto translation group.
Yes.
And then what we're doing,
you can form a condenser.
Yes.
And show that its capacity is not 0, or is infinite or not, depending on the case. Good.
Can you express this in terms of cohomology?
Well, not quite. Well, no better than what I did in the previous slide. Okay. Okay, that's the trick. I see. Thank you.
Thank you.
Sorry. Well, good. Thank you.
Thank you very much. Other questions? No other question? I have a question. So
Yes.
in this case, so the ones that you're just using the Durham differential. So you get the dimension n is equal to 3, and then the order of the differentiation is 1. Is that what?
Yeah, you're right. This is what this inequality reflects, right? Is that the differential for in any degrees is an operator of degree 1, and it's this one which is reflected here, and that gives this condition for Sobolev inequality to use, either locally or globally, when you have equality. And here, the degree of the differential depends on dimension, leading to this different expression. Does this answer your question?
Yes, but then like it's maybe you could get that they are different if it's sharp, right? Like you get the like if you can prove that the other, like if it's less than 1/3,
yes,
then it's gonna be
these statements are sharp.
Not for the like for the after like so I mean for that 1/3 is it also sharp?
Yeah, so well it comes exactly from that statement with n equals 3.
Okay.
Right. So
I'm also confused about the fractions, so
yes.
I don't know what but yeah, okay. And then just another question. So for the Kleiner-Müller-Ringsier, you're referring to the third paper, the one where they do just for the Heisenberg group.
Yes,
okay.
The one that deals with Riemann's complex.
Okay. Any other questions? If not, let's thank the speaker again. Okay, so we're ready for the first mini talk of the conference. It's Georg Gruetzner of Fribourg University, and he's going to be talking about Hilbert spaces attached to Möbius spaces. Thank you.
Yeah, thank you very much for the invitation for talking here at this beautiful conference. I will come back to hyperbolic geometry and will in fact attach Hilbert spaces to the boundary of hyperbolic spaces. And I must thank Luca again for introducing such a nice, giving such a nice talk on Monday. And we will a bit think back of that moment when he discussed with us of how to construct actually a visual metric on the boundary of hyperbolic spaces. And he talked, we learned in fact that when we do the visual metric construction and we sit at the origin here, then we get a metric on the boundary. And this metric will be actually just the Euclidean distance in the real case, or in the complex case, we learned that this will give us the Korani distance or the Sügel distance, how we are now supposed to call it. But now we can ask ourselves the question, well, what is if we don't sit at the origin, in fact, but what if we do the same construction of visual distances and we just don't sit at the origins, but at some other point? And what it turns out that we get a different metric, but this metric on the boundary will now have exactly the same cross ratio when we take 4 points in the boundary of that space. And once we have a set of metrics on the boundary for which such a number, the cross ratio is exactly the same, we call this a Möbius structure. And today we will, in this talk, we will try to use this Möbius structure to construct some Hilbert spaces on the boundary. So what's beautiful about hyperbolic geometry is that it has like this rigidity aspects on one hand, and it has which we saw before, where we have this geometry on the boundary, which in fact encodes the hyperbolic geometry in the interior space. But on the other hand, we not only have rigidity, but we also have flexibility properties which prevail in hyperbolic geometry, such as uniformization. We know Riemann's mapping theorem as a classical way, or Thurston's uniformization, or even what we learned, Balak-Bonk's theorem, which can be in some sense interpreted in this way. So in this talk, we will ask the question of, well, how flexible are hyperbolic groups in general, actually? And we will ask this question in terms of representation theory. And so I will phrase now this flexibility and rigidity ideas of hyperbolic geometry in terms of group actions. And a group we call flexible if there exists an affine isometric action on some real Hilbert space such that its orbit map is proper. And this property was introduced by Hagerup. Now, contrary to that property, we say that a group is rigid if, on the other hand, every affine isometric action on some real Hilbert space has a fixed point. Now, this is known as Cashtan's property. Cashtan's property is not exactly phrased originally in that way, but in that setting where we are today, we can take this to be equivalent. And then there exists even stronger forms of Cashtan's property T, where we replace now the Hilbert space by just most often. I mean, there exist multiple versions of this, but we replace it by some Banach space. And what we observe is that most hyperbolic groups, now if we look at the isometry group over the classical real hyperbolic space or the complex hyperbolic space, they are flexible in this sense of representation theory. Whereas SPN1, for example, this is the isometry group of the quaternionic hyperbolic space, or F4 minus 20, where we go to the octonionic numbers, where we have the Cayley plane, they in fact have Cashtan's property T. But what is also true is that in some sense, all of those hyperbolic groups, they do not satisfy stronger properties of this Cashtan property T. So one can ask the question if, well, could we possibly extend this flexibility property by a little bit and still include all hyperbolic groups? And well, one way to extend Hagerup's property was actually suggested by Shalom in 2001, which is by, well, replacing here the unitary representation with a uniformly bounded one. So if we have an affine isometric action, then we have this linear part and we have this non-linear part. And now in the affine isometric case, this will be a unitary representation. And the nonlinear part here will naturally satisfy this co-cycle condition. And well, this is what lives in the first cohomology, group cohomology, which we saw earlier also during this conference. And now the suggestion is, well, let's replace the unitary representation by a uniformly bounded one, but still ask for a proper co-cycle like Hagerup did. So proper meaning here that the norm of this co-cycle tends to infinity as G leaves every compact. And now the idea is to use the Möbius structure in order to construct such a uniformly bounded representation. Now, for the case SPN1, this conjecture is satisfied, and this is a recent paper by Nishikawa from last year. Nishikawa also mentions that Shalom has like unpublished results of this. I forgot to ask you, but well, and like there exists also a very recent paper by Vergara who shows Shalom's conjecture, in fact, in the case when we replace, well, we are not in the Hilbert setting, but we are in the setting of subspaces of L1. And in that case, even like Vergara is able to show that he can make this norm, can make this action almost unitary. So he can make this bound as close to 1 as he wants. And morally speaking, well, why does such a flexible, why have we such a huge flexibility on L1? It seems to be that, well, Hilbert spaces embed isometrically into L1, but in fact, like the whole situation between, when we're on this strip here between L1 and L2, the whole set LP case in that strip reduces, in fact, to actions on subspaces of L1. So as soon as we have one action on some LP space within that strip with a proper co-cycle, then we have one on some L1 subspace. So in some sense, we have a huge collection of spaces on which we can possibly find one of those actions, and this flexibility allows us to make this constant so small. Now, there exists like also strengthened form of Castellan property T. Like the most natural way to strengthen Castellan's property T is to go to the closest relatives of Hilbert spaces, which are the LP spaces. And then we ask the same question if every affine isometric action on some LP space now with P bigger than 2 has a fixed point. And for hyperbolic groups, we know that there exists some P prime such that when we let P go larger than P prime, this property will in fact fail, this FLP property. And P prime has, well, at least some geometric meaning. In fact, when we take P prime to be, P prime will be the conformal dimension of the hyperbolic group. But what is not so clear, in fact, is what happens now in this strip between 2 and P prime. Now there exists a theorem by Druto and McKay, which I give now like this without introducing the definitions. But here we look at Gromov density model of hyperbolic groups. And so what needs to be understood is that this theorem here talks about hyperbolic groups. And what is important is that they are able, in fact, to show that this P prime here, we can take as far to the right as we would like. And we can still find on such a strip here, hyperbolic groups, which are in fact rigid with respect to actions on LP spaces. So here, this constant here we are discussing Lipschitz affine actions. So this result, in fact, speaks kind of against our efforts to prove Jalom's conjecture, showing that, in fact, hyperbolic groups can be rather quite rigid. So at least it shows that in this case here, when we would like to have rigidity, we would have to have this Lipschitz constant to be at least bigger than 2. So, well, if we would like to prove Jalom's conjecture in the very general case of hyperbolic groups, we would like to get a Möbius structure, in fact, which we discussed in the previous slide for the general hyperbolic group. And well, to get a quasi-Möbius structure, we saw this already multiple times, is actually rather easy and straightforward. You go with the Gromov product, you take it like naively to the boundary by this definition, and then at least topologically, that's canonical, and you get a metrizable topology, whose metric is kind of squeezed between the negative exponential with some epsilon of the Gromov product. But K here might be bigger than 1, in fact. It turns out that we can make this K here equal to 1. And the idea is that when we let the hyperbolic group act on the Cayley graph, then we improve the word metric by smoothing the word metric on the Cayley graph by some measure. And the way this works is we start with a symmetric random walk on the Cayley graph on gamma, and we look at the probability that the random walk starting from G ever hits G prime. And now we take the negative log of this object and we get a number depending on G and G prime. And it turns out that this number is in fact a metric which is quasi-isometric to word metric or any word metric, in fact, and which is gamma invariant by construction and which is roughly geodesic. It's not exactly geodesic, so we have to pass to this slightly larger setting of roughly geodesics. And then when we now take the negative exponential and snowflake it by some epsilon, then this metric now, this new metric, will be an exact metric on the ideal boundary, which dates back to Nika and Spakula as an observation. Now there exists an alternative, much earlier construction, which is due to Mineev, which is more intricate, and so I choose to give this more intuitive picture here. Now, once we have constructed this matrix on the ideal boundary, now when we have an transform, when we change from O to some O prime, those metrics will in fact be in some sense conformal by having this, by satisfying such an equation. This follows by from below here. And this dO prime over dO is in fact just the limit of those metrics, which can be thought of in some sense like a conformal factor. And this here gives us something like a geometric mean value property between those two metrics. And once we have this, it's rather easy to see that once we produce the cross ratio with one of those metrics, then this object here, this number, will not depend on a choice of origin. And so indeed, we have this way a Möbius structure defined for any hyperbolic group. Now, originally, our idea was to get now like Hilbert spaces on the boundary, which are more or less Möbius invariant up to some bounded constant. So the naive choice would be, well, we just pick one visual distance and we look at the L2 space, but this construction will be far from being Möbius invariant construction. So a much better idea is to, well, look at maps from the group gamma to measurable functions on the boundary, and to choose to make the condition that they will change when you change origin by a conformal factor raised to the power of q over 2. And so if we take the square of those functions, those squares will transform exactly opposites to a measure. So if we integrate this with respect to the Hausdorff measure associated to the distance at O, this will define in a canonical manner a measure, in fact, on the ideal boundary. So this gives us a canonical L2 space definition on what we call 1/2 densities here. And this is in fact by construction a Möbius invariant construction, but the problem is that we don't have a cocycle, or we don't know of a cocycle sitting in 1/2 densities. But morally speaking, we can think of this space in some sense as the square of the measure space. And the measure space indeed has a natural, if we have the natural action on the measure space, then this gives us a cocycle already. And so the idea is in some sense to interpolate now between the L2 canonical L2 space for 1/2 densities and the space of measures which are 1 densities in fact. And we end up with a picture a bit like this, where we have here, this is one are the signed measures, 1/2 densities sit here in the middle, and we can indeed interpolate between them, which by spaces which are called S densities. So we take exactly the same definition we had before. We have maps on the group gamma mapping to measurable functions on the boundary, and we require them to transform with the conformal factor now raised to the S over Q. And so this here, let's say we are this space ds sitting here. Well, in fact, we have even a duality in here, which when we multiply now an S density here with the 1 minus S density on the other side, this gives us again a 1 density, and we can integrate it, and this gives us the duality between the two things. And in case of simple Lie groups, for those ones who know of rank 1, such a picture is in fact exactly what arises when we take the complementary series representation. Now, it was observed by Pierre that when we have now such a continuous density and we integrate it with respect to a kernel where we take the distance raised to the power of exactly 2q 1 minus s, then thanks to the conformality of this choice here, this will transform exactly like a 1 minus s density. So this is an operator which maps s densities to the opposite side of 1 minus s densities. And so now we can multiply them and we get a Möbius invariant quadratic form on s densities for any s between now here 1/2 and 1. And the tricky part about this quadratic form is, of course, its positivity. Well, as long as we are now in the real case or the complex case, so on the boundary of hyperbolic, real hyperbolic space or complex hyperbolic space, this quadratic form stays positive definite all the way until 1. And what Georg is doing is, well, he takes the derivative of this quadratic form at 1. And this gives us a positive definite quadratic form on the space of top degree forms which integrate to 0 and which is as well Möbius invariant. And in that case, we do have a co-cycle on that space, which by general principles will turn out to be proper. And so this is an explicit verification of Hargrove's property. Now, since we know that for the quaternionic case or the octonionic case, this can't work, there exists some S star, in fact, for which this quadratic form will become indefinite and fail to be positive definite all the way until 1. So the philosophical idea is, well, we replace this operator now with an operator which is not exactly Möbius invariant, but Möbius invariant up to a uniformly bounded error. And this way gain positive definiteness all the way until 1. And the inspiration comes from a paper by Stengo, Cowling, and Di Blasio, where they are in the Lie group setting of groups of rank 1. And they are looking, in fact, on this complementary series representations on this left-hand side on differential operators. And they construct uniformly bounded structures on that side for those spaces. And the way they do it, well, they take the conformal sublaplacian and they raise it to the power of alpha to the 2 over 2, and they take the L2 norm of that. And bounding this, in fact, is done by passing from the compact picture to the non-compact picture by a Cayley transform. And on the non-compact picture, we have dilations, and this is still dilation invariant. So this bounding this, in fact, in the non-compact picture is rather easy, and it reduces the problem of bounding this Cayley transform itself. Now, if we come back to Georg's operator, and we replace this S here by 1/2 plus alpha over Q, then we end up with an operator which looks like this, where this is Q minus 2 over alpha. And it looks very much like the fundamental solution of a Laplacian, at least in the real case. So the idea to follow Cowling would be, well, to replace this 2 alpha now with alpha and just apply it twice and take the L2. So taking the L2 norm, in fact, of this operator. And the hope is that this operator now, which is morally a root of that other operator, is still, this norm now is positive definite by construction, but still rather close to the Möbius invariant one, which is what this statement is in fact saying. So that there exists such a constant C. And this problem now, it brings us now into the world of geometric measure theory, in fact, where we would like to prove such a bound for such an operator, and we would like to phrase it in terms of a fixed background measure. And changing this norm now to a fixed background measure will amount to multiplying each one of those components with the right power of conformal factors. So this one with the right one, the density with the right one, and it will give us, will turn out that this is equivalent to proving a bound for the Georg's operator, which is conjugated by conformal factors raised to the power of alpha half. And some important technique, or in geometric measure theory, especially the Alphus-David regularity. And it turns out that when we have measures associated to a Möbius structure, then this Alphus-David constant can be taken uniform for all measures in that Möbius class. So we started off by trying to prove this more general statement. The problem is that we don't know much about this operator I0 alpha, in fact, especially so the only thing we are in fact able to prove is to prove that statement for a family of functions. And as a family of functions, we're taking certain powers of conformal factors and making use of the fact that this operator is a conformal invariant operator. So since it's a conformal invariant operator, this amounts to a certain amounts to the fact that we can take in principle this out, and this here will be more or less a constant function. It's just integrating 1 over the distance to some power over a compact space. And so this reduces now the whole problem to a problem on weighted LP spaces. And weighted LP spaces is something rather classical in geometric measure theory, where we have some measurable function which is considered as a weight to, with a measure. And the most classical question in that theory is, well, to understand when the Hardy-Littlewood maximal function is in fact bounded on some certain weighted LP spaces. And the condition was, so those weights were characterized in the 70s by Mukonopf, who gave a condition, a local bound on those functions. And in our case, we are interested only in those certain conformal factors raised to a power. And we allow us to have a certain P and Q introduced here. And each one of those integrals can be calculated directly and by uniformity of the Alphus-David constant. This gives a bound which is uniform, in fact, on that structure. And those general principles now allow us to give a uniform bound on the Giug's operator in the weighted case, and we get such a bound in that case for in this setting. And to give some perspectives, well, one thing to understand more is, of course, this operator I0 alpha, maybe in the case of trees, or to understand the difference. For now, we only know that on the functions. And there's also by Kevin Boucher some results on the other part here on the left-hand side. However, in the non-compact picture, so I don't know how it exactly relates, but it would be interesting to understand the other side here in order to discuss not only an integral operator, but in fact a zero-order operator, which would give more, which is more the classical setting in which of geometric measure theory where more general principles apply. Thank you very much.
Okay, so welcome back to today's final session. So the speaker is Robert Young from New York University, and he's going to be talking about surfaces in Heisenberg groups and quantitative rectifiability. Thank you.
Thanks. It's good to be here today. So the slides are going to be posted. The slides are on my website. Here's the URL, or here once I flip past this slide. So today I want to talk about surfaces in the Heisenberg group and how their geometry depends on the dimension of the Heisenberg group, and sort of how we can do analysis and geometry on surfaces in the Heisenberg group. And I want to give you some tools to visualize and understand surfaces in the Heisenberg group. So let me start with just a quick recap. So remember that the Heisenberg group, or the 2n plus 1 dimensional Heisenberg group, is a nilpotent group that can be written as a group of n plus 2 by n plus 2 matrices with ones along the diagonal, x1 through xn above the diagonal, y1 through yn on the right edge, and then a z in the top right-hand corner. This is a nilpotent Lie group with the Lie algebra that looks like this. It's got 2n plus 1 generators, x1 through xn, y1 through yn, and z, so that xi and yi bracket to z, and all the other pairs commute. There are a couple of ways to draw the Heisenberg group. One way is like this. We draw a picture of the Cayley graph. So the Cayley graph corresponds to the integer matrix. Sorry, we draw a picture of the Cayley graph of the integer lattice. The integer lattice is the set of integer points, integer matrices in the Heisenberg group. That's a discrete subgroup, and it's generated by, well, this is the three-dimensional Heisenberg group, so it's generated by x going like that, y going like that, z going like that. And you can see the structure of the Lie algebra come through in the structure of the lattice, because, you know, z commutes with y, commutes with x, z commutes with y, and if you take x and y, they don't commute, but their commutator, x, y, x inverse, y inverse, their commutator is z, right? X bracket y is z. So we usually put the metric, the sub-riemannian metric, on the Heisenberg group. Here's the picture of the horizontal distribution for the sub-riemannian metric. And one of the reasons we do that is because it gives the group a lot of symmetries. We have this scaling automorphism that's been talked about so much during the mini courses, which scales x by a factor of t, y by a factor of t, z by a factor of t squared, and scales the metric by a factor of t. We also have, and you can't really see it in this picture, but if we shift some of these cosets up and shift this up and down a little bit, we can get another picture of the Heisenberg group, which highlights the rotational symmetry. This is the same group. We've just changed the parameterization a little bit, and that change in coordinates gives us a symmetry which is rotation around the z-axis. So in H1, that's just the rotation group. In Hn, you can do the same thing to get the unitary group to act on Hn by isometries. It's okay? Okay, so like I said, today I'm interested in surfaces in the Heisenberg group. So let's start with smooth surfaces. If you have a smooth surface, then it has tangent planes at every point. And we can classify points on the surface according to their tangent planes. So if the tangent plane is horizontal, so I'm thinking about today I'm always going to be thinking about codimension 1 surfaces. So this is a 2n dimensional surface, 2n topological dimension surface. And so if the tangent plane is horizontal, then it coincides with the horizontal distribution. We call that a characteristic point of the surface. And then because the horizontal distribution is non-integrable, those points ought to be rare. Right? I think they're contained in like a codimension 1 subset. And otherwise, if we have a tangent plane which is not horizontal, then we can ask what happens when we take the blow up of the surface around that point. Well, if we have a point which is not horizontal, then if we have a tangent plane which is not horizontal, then the Heisenberg scaling scales the horizontal directions by a factor of t, the vertical directions by a factor of t squared. So if we zoom in around that point, the plane should tilt toward the vertical. The limit as we zoom in at a non-characteristic point is going to be a vertical plane. And we call that vertical plane the intrinsic tangent plane of the surface at that point. We should draw a picture because this can be a little bit it can be a little bit hard to intuit what these look like. So here's an example. Here's a horizontal plane for the origin, which is to say this is the plane where this is the plane which is tangent to the horizontal distribution at the origin. You can see that we call it a horizontal plane, but it's only horizontal at the origin. If we move away from the origin, it no longer coincides with the horizontal distribution. And so we can ask, okay, well, there's one characteristic point, which is the origin here. What do the tangent planes look like at all of the other points? Well, let's take a point over here, say. So I've drawn, here's the plane going like this, and then here we have the horizontal distribution. So again, the Heisenberg scaling is going to scale horizontal vectors by a factor of t and vertical vectors by a factor of t squared. So in particular, if we look at the intersection of the surface and the horizontal distribution at that point, the scaling automorphism is going to scale the horizontal vectors in the surface, the intersection of those two planes. It's going to scale those vectors by a factor of t. And not change their direction. They're just going to stretch out. But the directions that are outside the horizontal plane are going to get stretched to the vertical direction. So when we take that limit, the direction that's preserved is the intersection of the surface with the horizontal distribution. That intersection stays preserved. We just zoom in tighter and tighter. And so the vertical tangent plane, the direction of the vertical tangent plane is going to be given by the intersection between the horizontal distribution and the surface. In this case, in this case, if you take any point on this plane, the horizontal distribution through that point, the intersection is a radial line on the plane. You can see these in blue here. So what that means is that the direction of the tangent plane on this disk depends on where you are relative to the center. It's going to rotate depending on where you are relative to the center. Is this okay? Is this clear so far? Yeah? Okay. And the same thing's going to happen for more complicated surfaces. So this is an example of what's called a Heisenberg bubble set, which is, the Pansu made a famous conjecture that this is the isoparametric set in the three-dimensional Heisenberg group. It's got two characteristic points, one at the top right there, one at the bottom where you can't see it. And so near those characteristic points, it behaves very similarly to the previous picture where the tangent plane points toward the characteristic point. But then as you go from the top to the bottom, that tangent plane is going to rotate. And so as you go from the top to the bottom, it rotates from, I guess it rotates from pointing at the top characteristic point to, along the very edge, along the equator, the vertical tangent plane is equal to the Euclidean tangent plane. And then as we go further down, it's going to tilt again to point to the characteristic point at the bottom. So the direction that the surface points often isn't, it often behaves a little bit differently than it does in Euclidean space. So once we know the tangent plane of a surface, that lets us write the surface as a graph. In this case, we're going to write them as what surfaces as what is called an intrinsic graph. So an intrinsic graph, we call it an intrinsic graph because we define it using the group structure of the Heisenberg group. Because of the symmetry, because of that rotational symmetry, we can define this intrinsic graph for, in any direction we want, in any horizontal direction we want. I'm going to stick to defining an intrinsic graph in the xn direction, just because it fits very well with this picture. If our intrinsic graphs are just going to be graphs in the x direction, and so they're just going to be surfaces that intersect each of these red lines once. And so we define a bit of notation. Xn to the t is the one parameter subgroup generated by xn. Little xn is the xn coordinate function. And then if we have a function f on the plane xn equals 0, so the left side of this picture, we define the intrinsic graph of f as the set of points of the form v xn to the f of v, where v is in v naught. In this picture, this is literally, we take our function on the vertical plane, and we just take the graph in the xn direction. If you have a different picture, if you have that rotationally symmetric picture, then it's a little bit more complicated. But in this picture, it's exactly just the graph in the xn direction. Once we have that, so if you have a smooth surface and you have a vertical tangent plane, then you can write it as an intrinsic graph near that tangent plane, just by rotating that tangent plane to wherever you want and using the implicit function theorem. So once you have that representation, you can use that to calculate a lot of stuff about your surface. So in particular, you can use that representation to calculate the tangent plane, the tangent plane in the normal direction. Namely, for any other function g on the vertical plane, we define the horizontal gradient of g to be this expression. Grad sub f of g is the first n minus 1 coordinates are the derivatives of g in the directions x1 through xn minus 1. The second n minus 1 coordinates are the derivatives in the y1 through yn minus 1 directions. And then the last coordinate is the derivative in the direction of yn plus f times z. So this is a nonlinear operator. Or, I guess this is a, sorry, I shouldn't say that. This is a linear operator, but it depends on f. And the reason it depends on f is because of the non-commutativity of the Heisenberg group. The idea of this operator is that we have we have this intrinsic graph. We think of g as a function on that intrinsic graph, and then we want to know how that function changes as we move around in horizontal directions in the intrinsic graph. Because xn commutes with x1 through xn minus 1 and commutes with y1 through yn minus 1, most of those directions are easy to calculate. Most of those directional derivatives are easy to calculate because moving in the x1 direction in the graph is the same as moving in the x1 direction in the vertical plane. The exception is the last one because xn and yn don't commute because because the yn direction tilts as you go from left to right in this picture. That means that if we have a surface, say this plane on the right here, and we move horizontally in that surface, it corresponds to moving in a slanted direction in the original vertical plane. And so that's where, so it's in particular, it corresponds to moving in the direction yn plus f times z, and that's where we get this this expression here. So this tells us how g changes as we move around the graph of f. And in particular, if we look at the horizontal gradient of f, then that tells us how the function changes as we move around the graph. That tells us the slope of the tangent plane. Is this okay so far? Now, okay, so I want to define one more class of surfaces, and then I can explain the point of this talk. The last class of surfaces I want to define is what are called intrinsic Lipschitz graphs. And the idea of intrinsic Lipschitz graphs is that these are analogs of Lipschitz graphs in Rn. Like by a Lipschitz graph in Rn, I mean the graph of a Lipschitz function in Rn. And there are a couple of ways to characterize Lipschitz functions in Rn and Lipschitz graphs in Rn. And likewise, there are going to be a couple of ways to characterize intrinsic Lipschitz graphs in Heisenberg groups. So the standard characterization of a Lipschitz function is that if you have 2 points in the domain, then the difference between the values of the function at those 2 points is bounded by the distance between those 2 points. So what that means geometrically is that the slope of the chord between those 2 points on the graph is bounded. Another way of saying that is that this is a Lipschitz graph if we can draw some cone. So if we take any point on the graph, we can draw a cone where the angle of opening of the cone is bounded so that the entire graph lies inside that cone. And so we can do the same thing in the Heisenberg group. We can define a very similar inequality in the Heisenberg group. We say that an intrinsic graph gamma f is an intrinsic Lipschitz graph if there is some L, so that for every P and Q in V0, the change in the function at P and Q, the change in the xn coordinate between P and Q is bounded by L times the distance between P and Q. There's one little subtlety here, which just comes from the way that I've chosen to define this, which is that I'm requiring that my L be strictly between 0 and 1, and that my L be strictly less than 1. And the reason for that is that on the right side here, I have the distance between P and Q, and the distance between P and Q is always going to be greater than or equal to the change in the xn coordinate. So if L is equal to 1 here, this is a trivial condition, but if L is less than 1, then that's the same as saying that your graph lies in a cone, like in the Euclidean case. Is this okay so far? So remember when we define this graph, the point corresponding to V in this graph has xn coordinate f of V. And so that's what's going on here. The xn coordinate of P is a value of f, the xn coordinate of Q is another value of f, and we're saying the difference between those values of f is bounded by the distance between P and Q. Okay. So this is one way to define an intrinsic Lipschitz graph. Another way of defining a Lipschitz graph in Euclidean space is to say that is to bound the derivative. Like another way of characterizing a Lipschitz function in Rn is that its derivative is bounded. And we can do the same thing here. There's a theorem of Bigelin, Caravana, and Serracasano that an intrinsic graph is an intrinsic Lipschitz graph if and only if the horizontal gradient of f, you need to extend the definition a little bit because I defined it in the smooth case. You need to extend the definition to a distributionally defined version. But gamma f is an intrinsic Lipschitz graph if and only if the horizontal gradient of f is L infinity. So you can define intrinsic, so just like Euclidean space, you can define intrinsic Lipschitz graphs either in terms of a cone condition and an inequality, or in terms of a bound on the tangent plane, it's a bound on the slope. Again, I'm sweeping something under the rug a little bit here because this definition only works. This definition only works in exactly the context I've specified, where you have a function defined on the entire vertical plane. If you have a disconnected domain, then this slope condition doesn't work. And in fact, if you have a domain and you get too close to the boundary of that domain, again, this slope condition doesn't work. But in the context we're looking at, where we're looking at surfaces defined on all of V0, this definition works fine. And so these intrinsic Lipschitz graphs are like Lipschitz graphs in Rn play an important role in geometric measure theory. And likewise, intrinsic Lipschitz graphs in the Heisenberg group play an important role in geometric measure theory in the Heisenberg group. So for instance, Franchi, Serpioni, and Serracasano gave a definition of rectifiability related to intrinsic Lipschitz graphs. The set is rectifiable if and only if it can be covered by intrinsic Lipschitz graphs up to a set of measure 0. And so if you want to study rectifiable sets, or if you want to study surfaces in the Heisenberg group, the intrinsic Lipschitz graphs give you an important set of examples, and frequently and often you can take results for intrinsic Lipschitz graphs and translate them to rectifiable sets in some way. Is this okay so far? Okay. Oh yeah, I should show you a picture. This is a picture of an intrinsic Lipschitz graph, and so you can see, well, you can see this cone condition, or you can see, because the way I constructed this picture was to take a union of cones defined by an inequality like the one on the previous slide. You can see what those cones look like. They're sort of, they have to be scale invariant cones, so they have to have this z by z or t by t by t square scaling, and you can see that because of the shape of the metric on the Heisenberg group, because the vertical direction, distances in the vertical direction are much larger than distances in the horizontal direction, you can see that in the texture of the graph. As you move from top to bottom of this graph, the function oscillates very quickly. The function oscillates very quickly and very sharply. And in fact, the intrinsic Lipschitz condition only guarantees that the restriction to a vertical line is 1/2 Hodor. And so there are a lot of slices of this that look like the graph of a 1/2 Hodor function. On the other hand, if you move in horizontal directions, well, remember the slope of the tangent planes has to be bounded. So as you move in horizontal directions, the slope is bounded. And so you can imagine walking from this side of the graph to the other side of the graph along these ridges and just going up and down at a very gentle rate. The only thing to be careful about, or the main thing to be careful about, is that that horizontal direction depends on where you are in the graph. Like in this sort of valley here, the horizontal direction doesn't have very much z component to it, but if you walk along this peak here, along this ridge, you're going up in the z direction because of the change in the horizontal direction. Is this okay so far? Okay. like I said, all these pictures are in the slides. If you want to copy for yourself, it's on the it's at that URL. Okay, so what's the point? So what I want to do in this talk, how much time I have left, is I want to try to explain how this intrinsic Lipschitz condition depends on what dimension you're in. How intrinsic Lipschitz condition in dimension 3 is weaker than in dimension 5 and in higher dimensions. And so intrinsic Lipschitz graphs in the 3-dimensional Heisenberg group have wilder geometry than intrinsic graphs in the 5-dimensional Heisenberg group. Because of that, we need different techniques to study intrinsic Lipschitz graphs in different dimensions, its surfaces in different dimensions. In the 5-dimensional Heisenberg group and up, there's a nice slicing method where we can slice the Heisenberg group into copies of Hn-1 cross R. Whereas in H1, that doesn't work anymore. If we try to slice H1 into copies of H0 cross R, there's no such thing as H0. So that slicing technique doesn't work. Instead, we can study group graphs in the Heisenberg group by studying their horizontal curves. Okay. So just to start, let me give you a quick, simpler example of how this works. Let's take the strongest version of the intrinsic Lipschitz condition. Let's look at graphs where the horizontal gradient is identically 0. So let's consider some function f, which is intrinsic Lipschitz, and suppose that the horizontal gradient is identically 0. Then, when n is greater than or equal to 2, the intrinsic Lipschitz condition is strong enough to tell you that if the intrinsic gradient, the horizontal gradient, is 0 in a neighborhood of v, then the function is locally constant at v. But it's not strong enough in dimension 3. If n equals 1, then you can construct a wide variety of non-constant functions where the intrinsic gradient is 0 on the whole unit ball. And so how do we do this? Well, again, we use different methods in Hn and H1. In Hn, we have some very nice slicing methods. If we have a function like this without loss of generality, we may as well assume that the function is equal to 0 at 0, and that the intrinsic gradient is equal to 0 in a neighborhood of 0. What does that mean for the intrinsic gradient to be equal to 0? Well, all of these coordinates, the derivative in the x1 through xn minus 1 directions, derivative in the y1 through yn minus 1 direction, and ynf plus fzf, all those coordinates have to be 0 on a neighborhood of 0. This is a little bit difficult to deal with, but if we slice the Heisenberg group into smaller pieces, if we slice that vertical plane into smaller pieces, say we take the slice of the vertical plane where xn coordinate is 0 and the yn coordinate is t, then that's a very nice subset, because that if we set xn and yn, that gives us a coset of the subgroup generated by x1 through xn minus 1 and y1 through yn minus 1 and z. That subgroup is the Heisenberg group of 2 lower dimensions. And well, the horizontal gradient, the intrinsic gradient of f, tells us the derivative of f in all of these directions, in all the directions x1 through xn minus 1, yn through yn minus 1, the derivative has to be 0. So in particular, if I have any horizontal path in this slice, and because this is a copy of Hn minus 1, it's generated by, you can get from any point to any other point by horizontal paths in this slice. That means that f is constant along any of those horizontal paths. So it's constant on the entire slice. And in particular, the derivative in the z direction is 0. So now we have derivatives in x1 through xn minus 1, y1 through yn minus 1, and z are all 0. The only direction that's left is yn, but we know that ynf plus fzf is 0. Zf is 0, so ynf is 0. And so our function is constant on the entire ball. That doesn't work in the 3-dimensional Heisenberg group, because in the 3-dimensional Heisenberg group, you do the first step here. You have this 2-dimensional vertical plane. You slice it into 1-dimensional slices. Your 1-dimensional slices just generated by z. You don't have any horizontal directions in that one-dimensional slice, so you can't do anything. So instead, well, you can classify all the graphs in the three-dimensional Heisenberg group where the intrinsic gradient is 0 by looking at their horizontal curves. One nice fact about intrinsic Lipschitz graphs is that if you take any point on the graph, then you can find at least one horizontal curve through that point. You can show that if f is intrinsic Lipschitz, then for any v in the domain, there is a curve in the domain, which you can construct by taking an integral curve of the vector field grad f is y plus f of fz. And if you take such an integral curve, then the graph of that curve, which is to say, for each point on that curve, you translate in the x direction by f gamma of t. That's a horizontal curve in gamma f. So you can cover gamma f by horizontal curves like this. Furthermore, if the intrinsic gradient is continuous, then the derivative of f along one of these curves, the derivative of f composed gamma, is equal to that intrinsic gradient, right? Because the intrinsic gradient is trying to measure how the function changes as you move horizontally in the surface. But if you have these horizontal curves in the surface, that gives you paths that you can move horizontally in the surface. And if you differentiate along those paths, you should get the intrinsic gradient. If we have a curve like this, an integral curve of this field, we call it a characteristic curve. And we can characterize the graphs with intrinsic gradient equal to 0 by looking at these characteristic curves. So if the intrinsic gradient of f is 0, then that means that f is going to be constant along any of these characteristic curves. That means that the graph of that characteristic curve is a horizontal curve, and the x-coordinate of that horizontal curve is constant. But if you have a horizontal curve with constant x-coordinate, that means it lies in one of these vertical planes. That means it's, one of these blue lines like this, or one of these blue lines like this, or one of these blue lines like this. And there's no relationship. This gives us basically no relationship between different gammas. The characteristic curve through one point and the characteristic curve through another point. And so we can construct surfaces with this property so on one hand, any surface with this property is built from pieces of cosets of the one parameter subgroup generated by y. On the other hand, we can construct such surfaces by taking a union of segments of cosets. And so here's an example here. It's just made up of horizontal lines that are parallel to the what is that? That's the YZ plane. Okay. So yeah, so this is what I mean when I say that the intrinsic Lipschitz condition is a lot weaker in 3 dimensions than in 5 dimensions. One way that's true is that if we take the strongest version of the intrinsic Lipschitz condition, if we ask that the intrinsic gradient is 0, then that completely characterizes the surface in 5 dimensions, but it allows for this much flexibility in 3 dimensions. Okay. Okay. So yeah, the same thing is going to happen if we look at more complicated situations. Specifically, one of the projects I've been working on over the past couple of years is what's called quantitative rectifiability in the Heisenberg group. So to explain what that is, let me first say a couple words about rectifiability. So intrinsic Lipschitz graphs are rectifiable. One definition of rectifiability is that a set is rectifiable if it has a tangent plane at almost every point. And so Franchi, Serpioni, Sericasano proved that intrinsic Lipschitz graphs have this property. They have a tangent plane at almost every point. They satisfy a version of Rademacher's theorem. One way to state that is like so, let gamma be an intrinsic Lipschitz graph. And then it has a tangent plane at almost every point, which is to say, for almost every point, there's a vertical plane such that the limit as r goes to 0 of the Hausdorff distance between the intersection of a plane and the ball and the intersection of a graph and the ball is on the order of r. If we normalize by a factor of r, then this limit goes to 0. Quantitative rectifiability tries to study how quickly this limit has to go to zero, how fast the blowups of a set approach a vertical plane, approach the tangent plane. And this shows up in a lot of places in harmonic analysis and geometric measure theory and uniform rectifiability, because there are a lot of cases where we want to look at sort of, how complicated a surface is, how bumpy a surface is, so we can know, for instance, how singular integrals behave on that surface. And so with some collaborators, I've proved some results on quantitative rectifiability of intrinsic Lipschitz graphs in the Heisenberg groups. To state those results, I need one function. I need this function beta. So beta gamma xr measures how close gamma is to a plane on the ball of radius r around x. So this is we quantified this before in terms of the Hausdorff distance. We're doing essentially the same thing to define beta. We define beta gamma xr is the infimum over all vertical planes p of the average over the intersection of gamma with the ball of radius r of the distance from a point to the plane. So basically, we have some graph. We take the intersection with the ball. We look over all the planes, all the possible vertical planes, and we try to find the plane where the average distance to that plane inside the ball is as small as possible. So if this is, we normalize by a factor of r so that this is scale invariant. So if I take this whole picture and I scale it up by a factor of r, all these, this number stays the same. And the idea is that if beta gamma xr is small, then the surface is close to a plane on the ball of radius r. But if beta gamma xr is large, then maybe there's a sharp corner inside the ball, or maybe it's very bumpy inside the ball. In any case, it's somehow far away from a plane inside the ball. And so quantitative rectifiability results give bounds on this beta. So for instance, I proved a result with Vasilis Truziola, Sean Lee, that if gamma is L intrinsic Lipschitz, then gamma is close to a plane at most points and most scales, in the sense that if n is greater than or equal to 2, if we're in the Heisenberg group of dimension at least 5, then beta gamma satisfies this inequality. So just to go through this inequality briefly, we're looking at balls of radius between 0 and 1, which are centered in the ball around, in the ball around some point in the graph. And we weight those balls because this this integration with respect to dr over r means that we weight all the balls between radius 1 and 1/2, the same as the balls between 1/2 and 1/4, same as the balls between 1/4 and 1/8, 1/8, 1/16. Every separate scale counts about the same. And since there are infinitely many scales, this is saying that this number of beta gamma is small at most scales. So this inequality, this is exactly the same inequality that holds for Lipschitz functions in Euclidean space. For Lipschitz functions in Euclidean space, this is called Doron-Soros theorem. And it's really, in Euclidean space, it's really an application of the Pythagorean theorem. The idea is that if we want to take the graph of a Lipschitz function and we want to make beta large at one particular scale, if we want to make beta large at some scale r, then one way to do that is to take your graph and perturb it by something that oscillates at scale r. So I perturb it by something like this, so that if I zoom in, let me zoom in around that point like so. If I zoom in like that, this length scale is about r, and then the size of that perturbation is order of, say, epsilon r. If I do this, then, well, all my balls of radius r around any point in the graph are going to look about like this. They're going to be about epsilon away from a plane, which means that beta gamma xr is going to be on the order of epsilon. But if I take a much larger ball or a much smaller ball, it's going to be close to a plane again. So if I want to make this large, if I want to make this far from a plane at another scale, I need to do the same thing again. I need to add another smaller perturbation, say at scale s. Say at scale s. So again, the distance between here and here is going to be on the order of s. And then in order to get beta gamma xs to be on the order of epsilon, then I need that perturbation to have size about epsilon s. If I do that, well, this theorem, this inequality tells me that there has to be some limit to how many times I can do that. Because this inequality tells me that beta gamma has to be small at basically all but finitely many scales. So there has to be something that keeps me from just repeating this construction over and over and over. And that's the Lipschitz condition. Because if you have the graph of a Lipschitz function on in Euclidean space, the area of that graph is bounded. But every time we do this perturbation, the area of the curve increases, the length of the curve increases. How much does the length of the curve increase? Well, the Pythagorean theorem tells us that if we take a segment of length r and we perturb it by epsilon r, then the length increases by about a factor of, root of 1 plus the slope squared, 1 plus epsilon square, which is on the order of 1 plus epsilon square. So every time we do this, we pick up another factor of epsilon square in the length. And so the sum of all those factors, the sum of those epsilon squares, has to be bounded in terms of the Lipschitz constant. But that's exactly what we said in the inequality. The total of the squares of the beta numbers is at most a constant. Is this okay so far? I guess I could have about, 20 minutes? Okay, well, at some point I'm going to start flipping through slides very quickly. So this tells us that for the 5-dimensional Heisenberg group and up, intrinsic Lipschitz graphs behave very similarly to Lipschitz graphs in Euclidean space. That's not true for the 3-dimensional Heisenberg group. There's one small change in this inequality, which is that this exponent 2 becomes an exponent 4. And so in particular, in this inequality, you could have beta gamma on the order of epsilon at about epsilon to the -2 different scales, same as in Euclidean space. In this inequality, for surfaces in the 3-dimensional Heisenberg group, you can have beta gamma on the order of epsilon at epsilon to the -4 different scales, at many times more scales than in Euclidean space. So intrinsic Lipschitz graphs in the 5-dimensional Heisenberg group and up are about as rough as Lipschitz graphs in Euclidean space. Intrinsic Lipschitz graphs in the 3-dimensional Heisenberg group are rougher, or bumpier. And both these inequalities are sharp. You can construct intrinsic Lipschitz graphs that satisfy both of these. Is this okay so far? Okay, so how do we prove this? Again, we have 2 different methods depending on dimension. In high dimensions, we can use slicing. So let me show you how to do that. This is based on a theorem of Fassler and Orponen, who proved basically a version of Doran-Soros inequality for Lipschitz functions from the Heisenberg group to R. And the slicing argument that we did before lets us take an intrinsic Lipschitz graph in Hn and slice it into graphs of Lipschitz functions from Hn-1 to R. If I have an intrinsic Lipschitz graph in a high-dimensional Heisenberg group, then I can take that high-dimensional Heisenberg group and break it up into slices according to the yn coordinate. Each of those slices is isomorphic to Hn-1 cross R. And each of those slices, the intersection of the graph with any of those slices, is the graph of some slice of the function. It's the graph of the function over some subset of the vertical plane, which is isomorphic to Hn-1, right? You have a subset Hn-1 cross R. The slices of your graph are graphs of functions from Hn-1 cross R. And then the intrinsic Lipschitz condition on that graph gives you a Lipschitz bound on the function on each of those slices. Each of those slices Q naught T is a coset of Hn minus 1 generated by x1 through xn, y1 through yn, and z. The derivative of f in the x1 through xn directions and the y1 through yn minus 1 directions, those are all coordinates of the intrinsic gradient. So if the intrinsic gradient is bounded, all those derivatives are bounded, which means that your function is Lipschitz on each of those slices. And so the slices of the graph are all Lipschitz graphs in Hn minus 1 cross R. By Fessler and Orponen's version of Dor and Sorrow's inequality, Lipschitz graphs in Hn minus 1 cross R are close to planes at most points and most scales. They satisfy the inequality we want. There's only one problem, which is that, well, this tells us about individual slices. How do we know that if you go from one slice to another, maybe it's close to one plane in one slice, and then you move to the next slice over, it's close to a different plane. And so in the whole ball, maybe it's far away from a plane. And so we fix this with one more trick, which was we use this we use the isometries of the Heisenberg group. We use the fact that the Heisenberg group has this isometry group containing the unitary subgroup or the unitary group. So the isometry group of the Heisenberg group acts transitively on the horizontal vectors. And so there's some isometry of the Heisenberg group that takes this surface and rotates it by a small angle. If we take the surface and we rotate by a small angle, that's going to rotate all the tangent planes by a small angle. So if all the tangent planes stayed in some bounded subset, we rotate the graph, it rotates the tangent planes, they still stay in maybe a slightly larger bounded subset. And so if we rotate a graph by a small angle, and if we rotate an intrinsic Lipschitz graph by a small angle, it's still going to be an intrinsic Lipschitz graph because all of the tangent planes are still all the tangent planes stay bounded, the intrinsic gradient stays bounded. And so what we can do is we can take this whole picture with all these slices in the yn direction and then rotate it a bunch of times. That's going to give us a bunch of different sets of slices. And the same argument works for all of these slices. The graph is close to, the slices of this graph are close to planar at most points and most scales. And so you need a little bit more work to say that if you have a graph which is close to planar on a bunch of slices in a lot of different directions, then it's actually close to planar, period. But once you do that, you have the lemma, or you have the theorem. Is this okay so far? So we can we have this nice so in high dimensions we have the slicing argument. In low dimensions, again, we have to look at the characteristic curves. So recall, for any point in the vertical plane, there's a characteristic curve, so that the graph of that characteristic curve is horizontal. Because of the intrinsic Lipschitz condition, the x coordinate of that horizontal curve is a Lipschitz function. And in fact, the curve itself has bounded second derivative. If we write our curve gamma as, if we break it up into a y coordinate and a z coordinate, then the derivative of gamma is this vector y plus fz, so it's 1 comma f. But f of gamma of t is a Lipschitz function. So the first derivative of gamma z is a Lipschitz function. And so the second derivative of gamma z is bounded. So if we look at all of these characteristic curves, we have a covering of u0 by curves where the second derivative is bounded. Conversely, if we have a foliation of the vertical plane with bounded second derivative, we can construct a corresponding intrinsic Lipschitz graph. This is a little, let me just show you some pictures because it's easier to show the pictures than to do the calculations. So for instance, if we start with just a bunch of horizontal lines, the first derivative is 0, so it corresponds to the function where the x coordinate is 0, the vertical plane there. If we look at vertical at characteristic curves with derivative 1, it corresponds to a function with derivative with value 1. And as we move that plane back and forth, as we move our graph back and forth, the characteristic curves tilt either up or down depending on which way we move the plane. So in particular, if we start taking, so we can use this to draw a picture, another picture of the surface with intrinsic gradient 0 that we constructed before. Intrinsic gradient 0 means that the second derivative of all of these characteristic curves is 0. So they're all straight lines. And so if we cover a piece of the plane by straight lines, we get a surface with intrinsic gradient 0. What else can we do? Curves correspond to functions that change. Curves correspond to functions that change. So for instance, if we take this diagonal plane here, this plane with slope 1 here, remember the y direction in the Heisenberg group tilts as you go from left to right. And so as you go along this plane, that direction is going to tilt more and more. You're going to get a bunch of parabolas like this. And just to show you one more example. So the reason I say that this is almost a foliation, not exactly a foliation, is because you can have, it's easy to construct foliations by, or not foliations, collections of curves with bounded second derivative that branch and rejoin. So all these curves meet up at that point there. So there ought to be a singularity in the corresponding surface. What does that singularity look like? Well, in this case, the top half of the surface is a bunch of lines with slope +1. The bottom half of the surface is a bunch of parabolas like this. So that corresponds to lines with slope -1. And in the middle here, we have a bunch of parabolas that all go through the origin. So those should correspond to a bunch of horizontal lines going through the origin. And in fact, the surface we get is this. We take a half plane and another half plane and 2 pieces of horizontal plane in the middle. It's okay so far? So we can use this to construct a bunch of wacky surfaces. So we can build bumpy surfaces by perturbing a foliation. So we can start with just the vertical plane with x = 0, which corresponds to foliation by horizontal lines. If we perturb that foliation, it perturbs the surface. It adds bump to the middle of the surface. If we perturb again at a smaller scale, it's going to add more bumps to the rest of the surface, exactly like we did on the board there. And if we perturb again at a smaller scale and a smaller scale and a smaller scale, it's going to keep on adding more and more bumps to the surface. Now, so far, that's exactly what we did for Lipschitz functions. We just said, okay, we want to construct something which is far from a plane at many scales. So we just start with something smooth and add perturbations at smaller and smaller scales. What's the difference? What's different in the 3-dimensional Heisenberg group? Well, in Euclidean space, each of those bumps cost us epsilon² area. In the Heisenberg group, it's going to cost us only about epsilon⁴ area. Why is that? Well, in Euclidean space, if we wanted to construct a surface where which is epsilon away from a plane, then inside the ball, the slope of that surface had to be, plus epsilon minus epsilon, had to be on the order of epsilon. In the Heisenberg group, what we've just seen is that we can construct surfaces that are far from a plane, but the intrinsic gradient is 0, right? Exactly this construction where we take a bunch of lines and look at the corresponding surface. This is a surface with intrinsic gradient 0. So the area of this surface is exactly the area of that rectangle. There's no increase in area. Where does this epsilon⁴ come from? Well, the problem is that we can't extend this picture out to infinity. Because if we try to extend this picture out to infinity, if we try to extend this line out like this, and this line out like this, they're going to cross. And we can't have that. You can't have crossing horizontal, you can't have crossing horizontal curves on an intrinsic graph. You can't have crossing characteristic curves on an intrinsic graph. And so if we want to extend this out, we can't extend them as straight lines. We have to extend them as curves. We have to curve them so that they don't intersect. And those places where there's some second derivative, that contributes to the slope, that contributes to an increase in the area. And specifically, it contributes to an epsilon⁴ increase in the area, basically because if we want to take a bump function with depth epsilon, So that means the slope here is epsilon. And then we want to extend that out. The natural thing to do is to do that on a rectangle of length roughly epsilon inverse. Because in that slope, that gives this line time to come down to the bottom curve there and go up to the top curve there in a nice, gentle fashion. If we do that, then we have a bump on this rectangle of depth about epsilon, where the intrinsic gradient, the second derivative of these curves, is about epsilon squared. You know, the first derivative goes from 0 to epsilon to 0 again with epsilon inverse. So the second derivative is about epsilon squared. And if you have a curve with slope about epsilon squared, Pythagorean theorem tells you that increases the area by about epsilon to the fourth. And so that's where this epsilon to the fourth comes from. It comes from adding bumps like this, which are supported on very wide rectangles, adding bumps with very large, we call it aspect ratio, because the larger aspect ratio is a wider screen, right? And so by adding bumps with large aspect ratio, we can construct surfaces which make this inequality sharp. Is this okay so far? Okay. The difficult part is really the converse. It's proving that this is the best you can do, that this is the bumpiest object you can construct. I'm going to give you a quick summary. To prove that this is the best you can do, uses something called a foliated corona decomposition. The idea of this is that we want to take the domain of the surface and we want to cut it into rectangles. Where the rectangles correspond to the different bump functions that make up the surface. There are two difficulties here. One, in order for this to behave well with respect to the Heisenberg scaling, the top and bottom of those rectangles really ought to be characteristic curves. And two, because we know that we want to be able to construct bump functions with very large aspect ratios, the aspect ratios of those rectangles have to be able to get arbitrarily large. And so what we do is we define a way of cutting the unit square into pieces. We start with a partition consisting of the whole unit square. And at each step, we take each term at the bottom of our partition, and we decide, do we want to cut it along a characteristic curve, cut it horizontally, or cut it along a vertical line? If the piece is close enough to a plane, and the characteristic curves through that piece are close enough to parallel parabolas, then things look very nice and we can cut horizontally. If we have a piece where the characteristic curves are not close to parallel parabolas or where it's not close to a plane, then there's no point in cutting horizontally and we cut vertically instead. But the advantage is, if our surface is really bad, if our characteristic curves are really bad, eventually, if we cut vertically enough times, then the foliation in that skinny rectangle is going to be mostly left to right. And so the aspect ratio of the pieces of this partition is going to vary from as you go through this process, and it's going to vary from point to point in the surface. But the idea of the idea is that in places where the surface is bumpy, we do a lot of cuts along vertical lines, and the partitions get tall and narrow. But where the surface is smooth, then we can do more cuts along horizontal lines, and the partitions can get short and wide, get large, to get a large aspect ratio. The main thing we need to prove about this is that when we do this process, the rectangles don't escape. The rectangles satisfy some nice bounds. Specifically, they're going to satisfy this bound, that if we define the aspect ratio of a rectangle to be the width over the height, then, and if we weight the rectangles by the negative fourth power of the aspect ratio, corresponding to this epsilon to the fourth exponent before, then the total weight of all of the rectangles in this decomposition is bounded by a constant. Once you have that, that basically tells you that If you want to perturb if you want to perturb your surface, if you want to perturb it away from a plane, it's going to contribute to the left-hand side of this inequality. And so there's a limit to the amount of perturbation you can do before it stops being an intrinsic Lipschitz graph. Okay, so we call this Fourier-Corona decomposition. This is what we use for the to prove this inequality. Is this okay so far? Okay, very quickly. Some further questions. So this lets us study. So this is essentially the end of the talk. Let me just ask some further questions and show you some nice pictures. So we use these. So we use these surfaces and these inequalities to study embeddings of the Heisenberg group into L1. And we got the result that the Heisenberg group embeds with less distortion in L1 than the n-dimensional Heisenberg group or the 2n plus 1-dimensional Heisenberg group. We can ask the same question about other groups in other Banach spaces. It's related to proving quantitative rectifiability results for surfaces in other groups. We can try to do other analytical questions. We defined an intrinsic Lipschitz graph by saying that we want the intrinsic gradient to be an L infinity function. We could define Sobolev spaces. We could define functions with where the intrinsic gradient is LP, and we could ask what properties does this have. We can try to ask, all these questions were in codimension 1. We could try to ask similar questions for surfaces of higher codimension. And then one reason that I got into this, or actually, I guess that's not true. But one thing I'm interested in is the question of minimal surfaces in the Heisenberg group, and this gives us evidence that surfaces in the 3-dimensional Heisenberg group are wilder than surfaces in the n-dimensional Heisenberg group, and this is confirmed by other results. There's some results of Monti that show something similar, and so one consequence of this seems to be that we can construct minimal surfaces with a wide variety of singularities in the 3-dimensional Heisenberg group, but the 2n plus 1-dimensional Heisenberg group seems much more limited. So is it possible that minimal surfaces are different in the 3-dimensional Heisenberg group and in higher dimensions? And so I'll just leave you with some pictures of minimal surfaces. So this is a surface that was originally constructed, I believe, by Scott Pauls. I call it the herringbone surface because it's made up of a bunch of horizontal line segments like this, so that if you look at it from above, it looks like a herringbone pattern. So this is a minimal surface with a singularity all along one axis. We can modify this in a bunch of different ways. So Nicolucci, Golo, and Rittore constructed examples like this, where you have singularities along a Y shape. Basically, you take that herringbone surface and you cut it up into pieces and you reassemble them, and you get a surface like this, which is still minimal. You can construct minimal surfaces with boundaries. So this is so here the boundary is this curve here, where you have a vertical segment, a horizontal segment, another vertical segment, and then I've asked that the function go to 0 as you go out along the axis there. It looks like this. It's sort of a herringbone surface where the angle of the herringbone changes as you go from left to right. You can do other boundaries. So this is a surface with a vertical segment, vertical, horizontal, vertical again. You can see a piece of that same surface as before, but some other complications because of the boundary. Here's that broken plane again. You can ask, is this minimal? I mean, because it is, again, made up of horizontal lines, just like the previous surfaces. And it turns out it's not. It turns out that this is not minimal. And one competitor is this. I can't prove that this is minimal, but it certainly feels minimal. And one competitor is this, where it's made up of a bunch of pieces like this. One way to think about this is that you take this surface here with this singularity at the origin here. You take that singularity and you break it up into half a singularity over here, half a singularity over here. And so this seems to be the minimal surface with this boundary. But it's very difficult to, like, one of the main difficulties in working with minimal surfaces in the 3-dimensional Heisenberg group and in any dimensional Heisenberg group is that the deformations tend to be much more difficult in Heisenberg than in Euclidean space because of the nonlinearity in the definition of an intrinsic Lipschitz graph. And so there's no smooth deformation of this that decreases the area. basically because, you know, any smooth deformation of this is going to keep that singularity in some way. In order to reduce the area, you need to include deformations that break up the singularities in various ways, and we don't know how to do that in general. If you have an arbitrary foliation, not really foliation because you have these curves that can branch and rejoin. If you have an arbitrary collection of curves with bounded second derivative that cover the vertical plane, is there a way to smooth that out? We don't know, and that would be an interesting step in understanding minimal surfaces in the three-dimensional Heisenberg. Okay, thank you.
Thank you very much. Are there any questions?
Hi, good talk. The question is the following. Do you have some constructions of minimal surfaces in higher dimension, so in higher and Heisenberg group for n greater than 1? Some concrete example of most minimal surfaces?
A couple, but you know, a couple, but no, not much more. And we're like you can set up various functions, various z graphs in the z direction that are minimal, because there's a nice equation for z graphs being minimal. But you know, it's still, the smallest case is going to be 4-dimensional, you know, 5-dimensional Heisenberg groups. You're looking at 4-dimensional minimal surfaces, so you're solving some differential equation in 4 dimensions, which is hard to do numerically, at least. So we have some examples, but not nearly the variety that we have of.
I think about concrete analytic formulas of some, say, non-trivial examples.
Yeah. So I think Simona, where's Simona? Simona's constructed one. I have a student who's constructed another. There just don't seem to be that many.
Thank you.
So there are some constructions by Paul Young together with groups of others, exactly as you mentioned, through Riemannian approximations. And so there is a paper by Giovanna Citti, Maria Manfredini, and myself, where we look at minimal surfaces, intrinsic minimal surfaces, both in H1 and in Hn.
Okay.
And we have this dichotomy. We can prove this dichotomy. So we can prove it only for those minimal surfaces that arise as limits of Riemannian minimal surfaces. But then the constructions that Paul Young and co-authors built for this, they actually are through the minimal approximation. So because of a uniqueness theorem, there is this dichotomy that I think it has been proved already for this kind of theorems. Yeah.
Any other questions? If not, let's thank the speaker again.